60 years ago today, humanity looked up, beyond the confines of our world, and stepped outside. Since then, we've taken some small steps, had a look around the block, and begun to roam beyond it. Now, it's time to meet our neighbors, the Alpha Centauri system. Tantalizingly close, but guarding so many secrets. We know there are planets there, but how many are there? And what are they like? Could any of them host life? And can we ever step out far enough and fast enough to reach them? It's time to meet Alpha Centauri, our beckoning neighbor. Welcome to Breakthrough Discuss 2021.
And we would like to welcome Pete Warden, Chairman of the Breakthrough Prize Foundation and Executive Director of the Breakthrough Initiatives.
Well, good morning, good afternoon, good evening, everybody. A very exciting day yesterday. I'm particularly looking forward to today just as much as yesterday. I'm speaking to you today from Proxima B, as you can see in the background. Today we're going to talk about how to go to the Alpha Centauri system and where are we in that effort. But our keynote is an incredibly exciting keynote. I've known George Church for a while, and it was particularly taken a couple of years ago. We had a little mini conference at Harvard where he talked about the power of genetic engineering and what we can do with biology. And the idea of potentially actually landing on some of these objects and beginning to set up some sort of infrastructure and other capabilities. George is professor of genetics at Harvard Medical School, the director of the Personal Genomics Organization. So without further ado, Professor Church, over to you.
Show my video. I will be sharing a screen. Okay, there we go. And hopefully you're seeing one slide right now, not presenter view. And so this is about nanogram scale interstellar probes. I think you have online the abstract and the title. So this is intended to be speculative, but to encourage collaborations and questions. And I'm sure I will have many gaps here. Suggestions are welcome. So this is the abstract. The emphasis is on a spherical sail containing the payload. And I'm calling it nanogram scale because words like nanosat and femtosatellite have already been used for things much larger, sort of on the 28 gram scale. And there are two projects I just want to briefly mention. I consider them much harder than either the 1 gram or the nanogram projects. These involve the Genesis project, which involves all of the infrastructure of robotics plus all the infrastructure of a gene laboratory. So I think that's a bigger project. None of these are small projects. And then the self-replicating probes, which were first talked about by von Neumann, but more recently there's an initiative on this. But again, I think that since we don't have any example of a self-replicating system other than biological, that seems even harder. So anyway, back to the 1 gram and the nanogram. The 1 gram, you all know the goals and the general outline of that, so I'm just throwing it up here for a second. Aiming for about 0.2 times speed of light. So to compare acceleration, there's the various phases of this project. Acceleration is a challenge. For the 1 gram, it's various estimates around 60 gigawatts for 1,000 seconds, which is 60 trillion joules, and about $6 million per probe. Many of the numbers I'm quoting from other groups I'm sure have changed, so feel free to correct me. But the 1 nanogram is obviously 1 billion times less expensive, so we can use that to send 1 billion times as many probes. At least one group has talked about a 0.9 times speed of light probe. I think that would be even easier to achieve with something that's 1 billion times smaller. The angle that we need to be able to address, we'll see in the next slide, but the angles that I've seen in experiments on Earth are in the order of 10 to the minus 3 arc seconds, which is about 5 times 10 to the 9th radians. That doesn't mean we can achieve that in practice going that distance, but it just means we can do that in a laboratory setting. So after going those 4.7 or so light years, 265,000 times the length of Earth to Sun, we will need, in order to hit the small orbit of Proxima B, which is about 0.05 AUs, we need a precision on the order of 2 times 10 to the minus 7th radians, which is within the 5 times 10 to the minus 9th we mentioned. Some other off targets are other suns and planets which require less precision. Okay, so a spherical sail has probably been proposed more than once. The one that I have been referring to is from Avi Loeb, a fellow Harvard professor that I happened to stumble upon the reference. And it looks plausible. This particular simulation that they published, included in Astrophysical Journal Letters, had 4 Gaussian laser beams balancing, keeping the spherical sail in the middle. So in addition, there have been a number of papers on the kinds of coatings that you want, and quite frankly, I'm a little confused by some of this. They don't all seem to be saying the same thing, but I'm using this one as an example from the Atwater group. It's a nice discussion of multiple different kinds of composition. Shown here, crystalline silicon on the left and aluminum disulfide on the right, and then various kinds of metamaterials, multi-layer stacks and holes and so forth. So we would adopt something like those with further, I think, refinement would be required, since it's a radical change from a multi-square meter flat sail to a sort of nanogram scale spherical sail. So now we have the choices of flying by or landing with and without deceleration. I just put the landing without deceleration as an interesting consideration. Even going at 0.2 C rather than the 0.9 C that we mentioned briefly, it's been, you can do the math in your head, but it's around 4 trillion joules, which is about 10% of the Hiroshima little boy bomb. In contrast, a nanogram landing without deceleration, or not landing, hitting the atmosphere, would be the equivalent of, if complete deceleration would be the equivalent release of 1 kilocalorie in chemical terms, 1 food calorie in nutritional terms. It's not very much. But we don't want it to decelerate destructively, which almost certainly that 1 kilocalorie would do to a 1 nanogram. Instead, we don't want it to decelerate by hitting dust grains. Fortunately, the frequency of dust grains on that journey that we all know is about 11 orders of magnitude lower than the collision with hydrogen atoms and other small atoms and molecules. Hydrogen being by far the most common one at about 2 times 10 to the 5th per meter cubed, varying somewhat. And then the number of collisions, inelastic and elastic, is going to be somewhere between 10 to the minus 6 and 10 to the minus 10 square meters, meaning the size of the sphere. It could either be 10 to the minus 6 square meters would be very tightly around the 1 nanogram payload, while 10 to the minus 6 square meters would be something that show these 2 circles on the slide, show the scale of a tight one in the lower right and the larger one. And they give different collision cross sections and therefore different fraction of the deceleration, which would be due to hydrogen, versus the deceleration due to gravity and photon pressures, gravity-assisted photon pressures, as I cite here work from Heller and Hipke in 2017, where they estimate that for the kinds of sails they were talking about, which I think was quite general, it would be hard to decelerate more than 4.6% times speed of light. Now, if we decelerated it from whatever desired speed down to 4.6, by the time it gets into the vicinity of the triple stars, then we should be consistent with this Heller and Hipke estimate. So that would be a nice combination, is hydrogen plus gravity plus photons. Now it gets deflected by the photons into the nearest gravitational well, which hopefully is Proxima B, being deflected from Proxima star itself. Again, I'd love to have a discussion about the optimal coatings and surface area size. Now, as we look around our solar system, we see a lot of objects with more water than Earth has, listed in this graphic. But most of those would not be suitable for the sort of nanogram probe that I'm envisioning here, where the goal is to have it land into something that isn't necessarily suitable for life evolving or growing up to this point, but is suitable for our synthetic biological probe taking off. And that can be a variety of environments, but it probably isn't easy to do with these thick ice layers such as on Europa and Ganymede. If you look at Proxima B, we don't really know about the liquid versus solid water or any mixture. So these have a lot of liquid. These moons in our solar system have a lot of liquid, but a lot of solid preventing us from getting to it. But let's say there is some liquid somewhere on the surface of Proxima B. We still have problems that the photosynthetically active radiation is low compared to Earth, and there's a potential for a lot of radiation hitting, either sterilizing or possibly even stripping some of the atoms from the atmosphere. So it is technically possibly habitable temperature-wise, but there's these other issues. So we want to look at extreme organisms that deal with extremes. 2 that have been out in space due to human activity is this arid midge, polypedillium, which has been shown to tolerate from 3 degrees Kelvin to 375. 375 is just for short periods of time, but 3 is basically forever if you want, until it's thawed. It can tolerate up to 7,000 grays of gamma. Tardigrades are pretty similar, maybe a slightly broader temperature range. I think that's just the test. Maybe slightly less radiation resistant. But these are huge radiation resistance compared to, say, human, which is lethal at 5 grays. And they have various ways of tolerating desiccation and radiation, which is partially understood. But those are multicellular creatures with exoskeletons. Here we look at a different category of cells, which are typically single cell microbes, and they have some interesting properties. For example, here's one that goes up to 121 degrees centigrade, so would be above boiling if it were atmospheric pressure, but it's done at high pressure. pH 0, pH 12, nearly saturated sodium chloride, and even higher radiation, so 15,000 grays. They also have a variety of sources of energy, even if the sun is not available or adequate. There are many sources of energy on Earth that do not require organic material from other organisms, and also do not require solar energy. And I'll show a whole slide in the next slide. And there's examples of photochemistry, photosynthesis, at the very far red end of the spectrum in these two papers that I'm citing here. And so the justification for the 10,000 cells per nanogram, meaning this can carry not just one cell, but thousands of different kinds of cells if you want to deal with different kinds of environments, or multiple copies of the same subset of cells. So two photosynthetic organisms. Prochlorococcus is, most people have never heard of it, but it's the most abundant photosynthetic organism on the planet, including plants and algae and so forth. It's very small. It's a half a micron in diameter, 500 nanometers. It has no organelles. The smallest photosynthetic organism with organelles, meaning chloroplast, mitochondria, Golgi, nucleus, it's about 800 nanometers. Not that much larger, and still many of them would fit in there. And then just for reference, this is the largest cell, which is an ostrich egg. So this is a longer list of all the reactions that can provide energy if they're, assuming that there's any disequilibrium at all, due to this seismic activity or so forth. There's all these reactions to choose from, and we would want to have probably most of them represented one way or another in our payload, so that we're flexible with respect to energy source, because we're not going to bring it with us. Then we want to think about elemental abundance for building, not just for feeding the organism, but for building structures that are outside of the organism, things like lasers to phone home. And so here's some of the ones that I'm sure many of you are familiar with. I've just shown an example using yttrium and ytterbium in the next slide. So here's an example of one way of harnessing energy, in addition to the ones that I've already mentioned, where they harness it into their biomass, and then it can be released from their biomass in various ways, including electrical. This is a so-called seashell collector, and it shows that one of the natural forms of biomineralization that occur is also been harnessed by engineers to capture sun into a parabolic-like focus, and then that energy could be in one way or another channeled into a home-built laser. Unfortunately, there aren't that much literature on building lasers from dirt, but I think we should correct that absence in the literature. Anyway, this particular paper from 2005 on a 8% ytterbium-doped yttrium oxide, here they had to get to about 9 watts, had a 3 millimeter cube of this doped compound between two input and output mirrors and a chilling, keeping it at 0 degrees centigrade. All of this would have to be built by our payload after it had replicated to the point where it was capable of doing that. Now, this may be the most speculative or least believable part of my overall talk so far, but I'm going to try to justify why we think this is plausible and possibly in a shorter period of time than most people think. So here's just some semi-random examples of how synthetic biology can leverage a truly extraordinary combination capable in biology. So here's an example of one can transplant an eye into the tail of a frog, and it will connect up to the nervous system from a completely wrong place, and it will work well enough that you can do visual learning. And so that's in this paper here from Mike Levin's lab. Two other systems that we have engineered, and shown now at the molecular scale rather than at the eye resolution, is the ribosome on the left and the nanopore on the right. So these are composites. There are about 120 components that's required for the ribosomal cycling that's shown here. This is a nanomachine that we can engineer in a variety of ways that would take a whole nother talk to describe. The nanopore is a completely artificial combination of two different proteins, each of which has multiple subunits, which recognize, pull in double-stranded DNA, split it into two single-stranded pieces, one of which goes through the pore. So this either polymerase or helicase normal protein does not normally interact with a pore, but here we've made them interact, and it's a useful device. So both of these are useful devices that are highly engineered and were relatively easy to engineer because nature had done 99.9% of the effort for us. These would be extraordinary devices if we had to think them up and engineer them atom by atom ourselves. But fortunately, we don't, because they were a gift of nature, and we can keep harnessing additional things from nature. So here's an example of a retina, or actually an eye. You normally think of an eye as some millimeter scale thing that has many photoreceptors in it. But here's an example. This is entirely contained within a cell. This is just a piece of a cell. Here's a 1 micron scale, and you have all the components you expect of a classic eye, which includes the cornea, the lens, the iris, and the retina. And these are used to localize polarized light, ironically or interestingly, from the prey chromosomes themselves, the chromosomes that have enough structure that they polarize the light. So there's no getting around that. Your prey always have chromosomes. And part of this is due to stacked waveform membranes. So this is a 100 nanometer scale here, and it's a blow up of this large region in the middle here. It could also fabricate long lines that stretch from one end of the bacterium to the other, shown in this far left, of magnetosomes. So these are magnetic particles that help the organism sense up and down, or in principle north and south, by the Earth's very weak magnetic field, but these things are great at detecting it. So those are two kinds of strange materials. Here's another one. This is based on silicon dioxide and of course some proteins, where you get something, the moral equivalent of optical fiber, which has different refractive indices in the middle and the edges of the optical fiber. And this is used by the sponge at the bottom of the ocean, where it's dark. It allows a bioluminescent bacterium to send out a signal into the void to attract baby shrimp that can get inside of the basket, and then they're sealed in, a pair of them, mating pair, is sealed in for life. So that this is a complex 3 species system that helps perpetuate all 3 species. But again, you can see this refractive index engineering, I'm using as a metaphor, this refractive index that looks like it would be engineered but was evolved. Another example here is reflectance, quite relevant to today's topic. These are two beetles, one of which reflects green and the other reflects many wavelengths. And they do this by having this stacked or chirped stack of molecular layers where you can see they're very thick at the top, the external part where we're looking down on it, and all the way down to very thin layers. There's a 1 micron microscopy scale. And by the way, the refractive indices of the alternating layers are 1.73 and 1.4. If you decrease it from 1.73 to 1.56, you reduce the reflectance from 91% down close to around 50 or 60%. Conversely, if you increase the refractive index of the high refractive index, then you can increase the reflectance. So we don't know what the upper limit is for that, but it's at least 91%. And I think the final example, this is visual navigation in nocturnal insects. There are quite a few of them that migrate a long distance, but I'm taking here a non-migrating one where the dung beetle makes these nice spherical shapes and then wants to get them out as quickly as possible to avoid competition and predators and so forth. And it goes in a straight line and determines that straight line by looking at the polarization pattern of, or possibly other things, of the Milky Way galaxy. And this is done, so there's experiments that are done on all these migratory systems, birds and insects, where they'll use, for example, planetaria, even have floating planetaria. It's really quite great literature I encourage you to take a look at. But anyway, these ones have been shown even on new moon, or where the moon's below the horizon. You can see this exquisite following of straight lines due to the Milky Way. And then finally, after all those examples, I want to show you a kind of a progress curve that should help us think through what is reasonable to do in a short period of time to get this nanogram payload to do what we want it to do, and we'll of course test it on Earth and nearby planets and moons. We have, this is a progress curve for both reading and writing of biotech, synthetic biology, DNA, and it's improved over 20 million fold, most of it within the last decade, most of it at a rate which is much steeper than Moore's law and probably has not anywhere near done for reading and writing DNA. And this ability to read DNA in particular has allowed us to do bioprospecting, which means going through the biosphere, collecting interesting looking baubles and figuring out what they do, as well as we can by sequencing alone, and what we can't figure out by sequencing alone, then we can go into synthetic biology and start changing it. So it didn't come with an instruction manual, but it did come with an easy way of tweaking it and figuring out, reverse engineering what it does. And we're getting pretty good at both reverse and forward engineering. So, I mean, for example, an example is 20 million fold reduction in price, which is throughout all sorts of components in biology. One example is the human genome was $3 billion when we declared victory around 2004-ish, and now it's $300. So, and that was the 3 billion base pair was a poor genome, was not clinical grade. It was only half a genome really, and now very high quality full genome is 20 million times cheaper. So I'm going to stop there and look forward to the Q&A session later today. So I think I'm actually a little ahead of schedule here. Thank you. I'll stop sharing my screen.
Thank you very much, George Church, for that wonderful keynote presentation. So that brings us to the next phase of day 2 at Breakthrough Discuss 2021. And we will now be going to session 3, which is missions to Alpha Centauri. So I'd please like to welcome the chairs for session 3, Harry Atwater and Carrie Cahoy. Please, Harry and Carrie.
Okay, yeah, thank you, Jamie, and thank you, George, for that wonderful and thought-provoking presentation. I'm sure we'll come back to this during the Q&A with many questions. So we'd like to, first of all, introduce ourselves and then introduce the session. So I'm Harry Atwater. I'm a faculty member at Caltech. And as George indicated, I've been involved in some of the work on design and thinking about the Breakthrough Starshot light sail. And we'll have more to say about that later. So over to you, Carrie.
Hi all, I'm Carrie Cahoy. I am a faculty member in the Aeronautics and Astronautics Department at MIT. I work on very small optical communications demonstrations in space on CubeSats, as well as astrophysics and space telescopes that are used for the detection of exoplanets around other stars. I'm delighted to be here today and looking forward to this session about how we are going to get where we're aiming to go in getting to Alpha Centauri.
Okay, great. We're going to begin with just a scene-setting introduction to the session. So we'll start off and with a short introduction to session 3. So Carrie, take it away.
Sure. So what we wanted to do here is just kind of recenter ourselves into our normal daily lives and kind of do a quick exercise on scales. So starting with our homes, which are typically on the order of a couple hundred meters squared in area. And then we can think about our town, which is 50 kilometers, getting out to state size and, you know, having a little bit more governance and required coordination among large numbers of people to have infrastructure to make things happen. So that's kind of on the town and state scale, although there's a lot in the home too. And that's hundreds of kilometers. Countries really are very powerful in their combined efforts. 3,000 kilometers, and then continents are a bit bigger than that, so about 5,000 kilometers. So just kind of getting a sense of these scales and the amount of effort and coordination among us as a species that it takes to create an infrastructure and to make things happen. And then if we go to the next slide, we start to think about, okay, now that we have this population, this coordination, this cooperation, this force, where are we going to go from there? And what kind of collaboration over what time scales will it take for us to really expand our horizons outward significantly? And these are quite large distances and quite meaningful challenges. So if we're assuming that we're on the surface of the Earth, our house or our place is at a reference of 0 kilometers away. Our star system is, 150 million kilometers. Our star is 150 million kilometers, 1 AU from us. It takes light 8 minutes to travel. And so sending a command and hearing back what happened at that distance would take 8 minutes. And it's 4.3 light years to Alpha Centauri. So that's kind of like sending your kid off to college and not hearing how he got there and how well he's doing until he graduated. It's kind of what it's like to try to do mission operations at that distance, and that's traveling at the speed of light. Our vehicles to date can't quite go that fast. We can travel on the order of tens of kilometers per second today, and so there's a lot of innovation that Harry and others have been working on to try to get us to more relativistic speeds so that we can get there faster within decades instead of hundreds to thousands of years, and try to convey our findings back while there are some of the organizations and infrastructures in place that design them that would like to hear about them. So that's the goal. The galaxy, the Milky Way that we're in, is about 50,000 light years across, with Sagittarius A at the center. And the universe is more expansive than that. So if we go to the next slide, so that is 46 billion light years across. So this is just showing kind of where we are in the galaxy. So you can kind of see the center. And we are on one of the spiral arms called the Local or Orion arm, and that's our solar system right there. And then if we go to the next slide from there, further out, That is the known universe, which is 93 billion light years across. So half distance is that 46-ish number. And we're really, really close to the center. So that Virgo supercluster is where the Milky Way is. And so on the grand scale of things, getting to Alpha Centauri is still like a tiny little hop in this enormous expanse that we have to explore. And some of our speakers today will talk a little bit about what's out there and the tools that we use to explore and understand it. And others of our speakers will talk about how we're going to get there and how we're going to exchange data to convey information from one place to the other. So I'll turn it over to Harry to continue the journey.
Okay, yeah. Well, they say in life that satisfaction should be derived not from the destination, but the journey. And indeed, today is all about the journey. But if we now think about just from this humbling introduction that Carrie gave us, the time estimates to get to Alpha Centauri, we can see that at tens of kilometers per second, the speed of chemically propelled spacecraft, while it's tractable to go to our outer planets, and such as was achieved with great triumph by the Cassini mission. It's essentially totally out of bounds to think about using such spacecraft to get to distances as close as our nearest star system. So we really, the current way of space exploration is not scalable to interstellar distances. And that was recognized by this audacious and forward-looking group of people in 2016 who were responding also to the excitement around the discovery of the Proxima B, reported and the explosion of information about exoplanets. And that gave rise to the inception of the Breakthrough Starshot program. And just, I'm sure many, if not most of the audience are aware of what we call the point design, the point 2Z point design mission. There are in fact many missions that could be contemplated by a radiation pressure laser-driven light sail, but the Breakthrough Starshot mission contemplates a photon engine with a total power of the order of 100 gigawatts at about 1 megawatt per square centimeter. That's, to an optics person, that's a relatively modest power, actually. At a wavelength of 1 to 1.5 microns, with a phased array laser system shown here, both before and after it's turned on, with a kilometer scale aperture, producing a beam to propel a gossamer-like thin dielectric membrane light sail across an impulse of about 1,000 seconds up to a speed of 20% of the light speed, across this journey of 4.2 light years, requiring about 20 years time for a gram scale payload with a gram scale light sail contemplated. So one thing I thought I would do is, just for the benefit of the audience, there's been a tremendously prolific activity in design and imagination of the concepts for the photon engine, the light sail, and beginning very recently also the communications systems required. So I thought I would just give a few sort of high-level observations, and these are purely mine. But what have we learned since 2016 about the feasibility and the viability of some of the concepts involved? And I think on the photon engine side, I think so one piece of very exciting news is that there's a viable concept for power combining in large phased arrays at the scale that's required. Second, the light source of choice that we would use, solid-state lasers made with semiconductor diode lasers, are following a classic technology progress curve. That is, the more you make of them, the cheaper they get. What that means is that the costs for the lasers that are required can follow a predictable curve, and once we can project how many lasers are needed and what the volume of production is, we can assess whether this can be done in an economical fashion. And I would note that there's a lot of tailwind in the laser technology evolution, driven by lasers in communications, and very shortly, likely also the penetration of lasers into general lighting, which are now dominated by LEDs, and that would greatly stimulate the production of solid-state lasers. The light sails, just to sort of reflect on some of the questions that James Cameron asked yesterday, there are in fact available to us today ultra low loss materials that can be synthesized as light sail membranes. And because they have ultra low optical losses at the pump wavelength, these can be tailored to be thermally stable by radiative cooling. So there's a balance between pump absorption and radiative emission that determines the temperature of the light sail. And it looks like this is actually a manageable idea to do thermal management. And the sail designs that have been developed indicate that some of them are consistent with stable launch trajectories. So that's quite an interesting concept, which means that we ought to be able to control light sails despite their thin membrane-like structure along the trajectory of the optical axis of the pump beam. So today we want to note that we have an exciting panel that will span many of the issues required to consider during the journey, including light sailing to interstellar distances from Arthur Devoyan. Stephanie Millam will tell us a little bit about the challenges and the opportunities associated with the interstellar medium. Michael Palusek will discuss with us an alternative to light sailing, which is a fusion proposal for Alpha Centauri missions. And Thomas Roberts will tell us about the current state of deep space optical communications, which is the go-to next generation method for communications being employed in future spacecraft for NASA missions, for example. So with that, we'll turn to our first speaker, who is Arthur Devoyan. Arthur is an assistant professor at UCLA. He's a master of metamaterials and photonics, and will tell us about concepts related to extreme light sailing the materials under extreme conditions.
Thank you, Harry. Thank you, Kerry, for the introduction. It's a very exciting set of slides that you showed. So let me share the screen here, and hope you can see it now. Screen. Okay. So Harry and Kerry essentially challenged me with a very difficult task of trying to understand how can we get to Alpha Centauri, which is this star on the left from the in this picture. And really, if you think about it, the scales of the distances that are out there, and as Harry showed, we have learned so far how to travel to planets in our solar system, and these are the number of missions that we have had so far to neighboring planets, Venus and Mars. Obviously, these are close to us, so we have explored it quite well. But as we go further away, Jupiter, Saturn, we see that the number of missions is actually kind of quite small. And in fact, beyond Saturn, the outer planets, Neptune, Uranus, they have been visited only once. And we have only 2 probes, operating probes. So 4 left the solar system, 1 is on the way, and 2 operating probes, Voyager 1 and Voyager 2, that have exited the solar system, the heliopause boundary, just quite recently. And with the speed, and the Voyager 1 is actually going at its maximum speed, the record speed, heliocentric speed, 17 kilometers per second. So with this speed, it will take us about 79,000 years to essentially go to the Alpha Centauri that is in here. Now, what happens is that if you think about it, what was our civilization look like 79,000 years ago? Actually, I checked yesterday. So Neanderthals were still here, and it's more time than what our civilization has had so far as a concise civilization, right? So we want to go faster, and really the reason for that is basically to try to understand whether there is life out there on neighboring planets, and tentatively the Proxima Centauri B, a planet, an exoplanet that is closest to us, that happens to be the closest to us, is likely to be in the habitable zone. And if we understand how to go to the Proxima Centauri B, maybe we can also go to other planets that are closer and try to learn and explore space around us in the neighborhood. But there is a big challenge, and that's actually our way of exploring space and the way we travel in space. So what you see here is the rockets. It's the main way of going to other planets. So for example, if we launch the missions to Mars, Venus, or whatever it is, we use rockets. And the way the rockets work is that they expand the fuel, expel the fuel from the nozzle with very fast speed at about 5 kilometers per second and so on. But what you see here, what they kind of try to circle out, is that most of the rocket, 90% of the rocket, is actually the kind of dead weight in some sense. It's the fuel and the structure, and it's only a very small fraction of that that goes to the actual useful, as we call it, payload, or the spacecraft that is in there. Now, the key problem, fundamentally, the key problem with rocket technology is that the power and the propellant, they're both on the board of the rocket, and we have to carry it with ourselves, and that's limiting us in the end. So if we put it into the numbers, basically, a very simple way to think about it is the rocket equation, Tsiolkovsky's rocket equation. If we do the numbers and the math, we see that the velocity that we can gain is related to the mass of the fuel that we need to expand and throw it away, as well as to the velocity of the fuel that's coming out of the rocket nozzle. So if we do the math for the rocket, chemical rockets or electrical engines, we see that the maximum that we will get is the mass that we need to put into the system as a fuel is actually ginormous, right? So if we want to propel, for example, or launch a 10-kilogram payload, we need really excessive mass for the fuel. It's not comprehensible just to get to 10% of the speed of light. So we need something different and something new here. That's where the light sailing comes into play. So kind of a brief introduction here. The idea is that we will have some sort of very thin and lightweight sheet membranes of dielectrics or metals that would be pushed by photons. So here in this case, the power and the fuel, that is the photons itself, the propellant, they are outside of the sail, they are off board of the spacecraft. So the spacecraft is just kind of useful mass that is out there, as much as we can have in there. And therefore we can potentially, conceptually speaking, propel it to very close to the speed of light, as we heard from the keynote talk, to 0.9% of the speed of light. For the Starshot mission, we are thinking of 20% of the speed of light. So here's a breakdown of the Starshot mission that Harry has introduced. The idea is that there would be a kilometer scale laser array with 100 gigawatts of power, illuminating a spacecraft with a light sail on it and propelling it within 20 years to the Alpha Centauri system with 20% of the speed of light. So the challenge here, many challenges, there are a lot of challenges existing here, but essentially they can be grouped into 3 different categories. How do we build 1 kilometer scale array? And we heard from Harry that it seems to be doable. We just need more development in that area. Communication. So once we reach the Alpha Centauri system, how do we send a signal back? We don't know that yet. That's an ongoing research area. And the light sail. How do we design an efficient light sail? So here are some of the points of the challenges that I have summarized for each of these different areas. And it would take maybe another 2-3 hours to discuss each of these points. It's like really very exciting and very active developing field of research. But let me just give brief highlight of where we are with the light sail technology. So we think about the light sail. What do we really want and need from a light sail to go to the 20% of the speed of light? We'll see that just a kind of single thin film membrane of material with a regular density of the material, say for example silicon. Then to go to the 20% of the speed of light, we would need a membrane that would be about 50 nanometers thick, right? So that's very thin membrane of material, and the power at around 100 gigawatts. So that's a lot. So how do we create a membrane that reflects all of the light very efficiently, so that we can use the radiation pressure and propel the system? So back a couple of years ago, Harry and I and other team members that we have, we looked into different materials and configurations in here and figured out that by nanostructure and using metamaterials approach, we can really get to the systems that reflect light efficiently with 100% efficiency. And unfortunately, these systems then would weigh a little bit too much, 5 to 10 grams, whereas we want to go to 1 gram limit. So we came up with a trade-off formula, which is trying to optimize for the distance, for the acceleration, for the optimal acceleration, rather than the mass of the sail material, and figured out that we indeed can get to the regimes by properly structuring these materials and structures in here. So currently, in my group and many other groups, we are working on trying to see how can we fabricate these. One of the material candidates that we heard is the molybdenum disulfide. It's very much the graphene-like material, very thin. You can exfoliate into single atomically thin layers. And by nanostructuring, for example, like here, you can see a photonic crystal-like system that would be a thin membrane, just 30 nanometers thick, that would reflect light quite efficiently. Here is another demonstration from my colleagues and collaborators at the University of Pennsylvania. What you can see here is a very thin backbone of alumina, ultra lightweight. The scale is 20 microns in here. And on top of that, this pinkish color is an ultra light thin film material of the molybdenum disulfide that is deposited on it, and so on. So these are very lightweight structures. The idea of the slide is that we really can do this light sail material, as Harry pointed. So we are close to having it quite soon in our lab. Beam stability, beam riding stability is another issue and challenge. And by structuring it at the nanoscale, again, with the same approach of metamaterials, we can have flat sails that can really stabilize on top of the beam. And here is a simulation and calculation that we did several years ago. And it really shows that we can have planar sails that glide out there. So it seems to be doable and out there. But let's kind of take a look at the scales again. So this is our goal, the Alpha Centauri. At the same time, the record-breaking speed that we have is 17 kilometers per second. So we're talking about two different regimes on the very big end of the spectrum. So 17 kilometers per second, something that we have right now, and 20% of the speed of light, that's our goal, right? So we have nothing in between of these two. So Voyager is the fastest. It took 35 years to go to 120 astronomical units. So can we go somewhere in between? Bring up this slide with the speed versus the sail thickness. With power, we see that there is range of velocities that we have never achieved so far before. So this is the record, the dashed line is the record. This is our goal, and that's a logarithmic scale. So on this logarithmic scale, there is really large gap of velocities that has not been achieved yet. So by reducing and relaxing a little bit the conditions of the power and the sail material, we can see that we can try to get into these regimes. And that's what we explored in my group. So one of the concepts that we're thinking is a wafer scale spacecraft, also envisioned by some other people, some other groups. Here we would use much lower power and a wafer where we can deposit everything, electronics and all of the materials and components within it, on top of it, where another side would be a sail, and then we can propel it. So in my group, we have looked into this in detail, and we see that because of the relaxed conditions, we essentially can now optimize the sail quite efficiently, because the sail material becomes much smaller than the payload, than the useful part of the sail, or than the useful part of the spacecraft. So our sail mass is about 0.1 gram, and the total mass of the entire system is about 1 gram. We can optimize it very efficiently to have reflectivity about 100%, and withstand powers in the range of 1 megawatt, 10 megawatt, with temperatures of this entire sail material less than 500 Kelvin. So that's very doable technology. What this chart on the left shows is that with 1 megawatt per gram, we can by far exceed what we have achieved so far with chemical engines and electrical engines. So the metric that we use to understand the figure of merit for us to understand is the delta V, the gain of the velocity that we can get in space once we launch the spacecraft. How do we change the velocity? So far, the largest figure of merit was achieved by Dawn spacecraft in 5 years. With laser propulsion, we can get it in 2,000 seconds essentially exceed what we can get with a domed spacecraft. And that's quite interesting because it paves the way to interplanetary missions. For example, what you see in this chart is the time of flight to different planets for different power levels. And essentially, if we use lasers that are 100 megawatts in power, 50-meter aperture of the laser array, then we can see that we can get to Pluto in about 24 months, Mars in 1 month, Jupiter in 3 months. So that paves the way to exploration of the interplanetary distances. But light sailing, laser sailing is not the only technology that uses photon radiation pressure. Solar sails, they also are out there, and we have seen many successful solar sail missions flown in previous years. Solar Cruiser is the most recent one, and it's planned with a very large sail area, the largest so far that has been envisioned. So in my group, we are thinking of using solar sails to do the very fast space exploration. So we're thinking of sending a sail very close to the sun, use a powered gravity assist of the sun, where the gravitation of the sun and the radiation pressure coming from the sun, they interact together to propel the spacecraft to very large velocities, to more than 50 astronomical units per year. And we think that we can send probes, 10 to 20 kilogram probes, very fast velocities in here. In this case, we will surpass the Voyager in just 2.5 years and reach 2,000 astronomical units in about 20 years. So yes, and here is the kind of little bit of numerical values of that. So the velocity that we can achieve versus the distance from the sun, how close can we get, and the light and the lightness of the spacecraft. So really, we can get to 60 astronomical units per year, which is about 0.1% of the speed of light. So thinking in terms of the roadmap, that's my last and concluding slide. Thinking in terms of the roadmap, so this is where we are now. The Voyager, 17 kilometers per second. We want to get to the Alpha Centauri system, which is 20% of the speed of light. And really, in between, there is pretty much nothing. Laser sailing can open all of this space of velocities for interplanetary and interstellar missions. And solar sailing can serve as precursor missions to probe the interstellar medium and bring the important data that is out there. So we can see that we can do the fast exploration of the planets and so on. With this, I would like to thank Harry and Kerry.
Okay, great. Thank you, Artur, for that introduction to light sails, both driven by lasers and sunlight, or perhaps someday also starlight. And our next speaker is Stephanie Millam, who, I think every kid always wanted to be what Stephanie is, which is an astrochemist at the NASA Goddard Space Flight Center. She's an expert in spectroscopy and laboratory modeling of the interstellar medium, and she's going to tell us about what we might encounter along the way to Alpha Cen in the interstellar medium. So Stephanie, take it away.
Okay, can you hear me?
Yes.
Yep. Right. Let's make sure this is showing. Okay, hopefully you can see my slides. All right.
Yes, we do, yes.
So thank you so much for having me. I am sort of the, outlier in this group of speakers today. I am an astronomer, an astrochemist at NASA Goddard Space Flight Center. And I'm going to talk to you a little bit about the local interstellar medium, so our nearest neighbor, and basically some future missions that are on the horizon that's going to help us study this area even more, giving us some context for a mission, potentially to the Alpha Centauri system, but also maybe a little bit more detail on how to do things in the future. So again, thanks for having me. So first things first is what we already know. All the observations beyond our solar system, or what we know, is based on remote sensing. we are exploring our solar system as best we can. In the most detailed, of course, there's going to be somebody doing some service on my house as I'm speaking. So we have a number of missions that have been basically spanning the vastness of our solar system, and it is quite vast compared to what we know locally, just as far as the terrestrial planets go and out to the Kuiper Belt. But what we want to do is actually break beyond this region. And how do we do that? And the key is we're working on this as best we can, and we have been for quite a while now. Starting back, with the Voyager missions. Voyager 1 is now the farthest man-made object from Earth, and as of April 10th at 148.42 AU. Voyager 2 is also still out there. It's been past the heliosheath since 2007 and has actually entered interstellar space beyond the heliopause around 2018, the end of 2018, and still on its journey. We also had a number of Pioneer missions. Unfortunately, these are no longer in contact due to discontinuing operations or just losing reception. So this is sort of where we are as far as getting as far as we can from our own local solar system interstellar medium. So to leave the solar system, we actually have to go through quite a bit, and actually it is quite challenging. And as a planetary scientist, I can tell you we want to explore even the outer solar system. So thinking even beyond leaving the solar system is something that's quite abstract for even somebody working at NASA on solar system missions. So we have to get outside of it. We have to break beyond the heliopause and the termination shock region. We have to get through the hydrogen wall and barrier. Hopefully pass by a couple of small bodies in what we call the Oort cloud or Kuiper Belt region, and maybe get a little bit more data on those types of objects, which are very interesting, before we actually even think about breaching the Alpha Centauri system. This is quite an extreme region that we have to actually break through, because we have to get through this whole astrosphere. These are really cool things, and we actually can observe them in other systems. So this is where the solar wind and the planetary system is actually interacting with the local ISM, and you see these huge astrospheres or arcs that we can actually measure and observe at various wavelengths. So you see a couple of visible images here on the top, as well as an ultraviolet one on the bottom. But we do know a bit about the local interstellar medium, thank you to some very sophisticated telescopes and missions, both ground-based and space-based. So we know the sun's inside this tenuous cloud, which is called the local cloud. And they're identified, the clouds themselves are actually identified by their motion, which we can measure with high sensitivity instruments. Our local cloud is actually known as the local fluff, which is quite a fun term and nickname. It actually has a temperature that's about the same temperature of the sun. It's quite hot, it's 7,000 degrees Kelvin. It has a density that's quite diffuse, as I said, at 0.3 atoms per cubic centimeter. And if you want to compare that to the local interstellar medium, that's a little bit more dense at 0.5 atoms per cubic centimeter. Or our local bubble, which is actually very diffuse and sparse. And actually you can see sort of the dark streaks in this image showing you how diffuse it possibly can get. And that's at about 0.05 atoms per cubic centimeter. So this is an image showing you where everything is sort of with respect to each other, including our solar system. That yellow dot of the sun actually shows you about the scale of the Oort cloud. So you can see we still have quite a bit of distance to go beyond our own Oort cloud just to get to Alpha Centauri. And this is an image that was acquired with the NASA Interstellar Boundary Explorer mission, or IBEX. So Alpha Centauri itself is our closest planetary system. It's 4.37 light years away from the sun. It's a triple star system with a binary, Alpha Cen A and B, which are class G and K stars respectively, and Proxima Cen, which is a class M star. So Proxima Cen is the closest star to us at 13,000 AU, it's 13,000 AU from the binary, Alpha Cen A B. And there's a number of planets that have been identified in this particular system, and some still yet to be confirmed. You can see though, with respect to the sun, these stars are, well, at least Alpha Cen A and B are pretty close to what we know of our sun, or have measured with the sun, and then Proxima Cen is actually quite small in comparison. So to date, our state of the art is actually somewhere around the Hubble Space Telescope. And this is the best image that we've acquired with Hubble of Alpha Cen A and B. And you can see that they're spectacular stars. They're nice and bright, which is fantastic for doing detailed studies from the ground. But it's quite challenging the bigger and more advanced our technology gets and the sensitivity of telescopes gets. Because they are so bright, it leads to a lot of challenges for trying to actually measure things like planets around these bodies. But if you go to longer wavelengths, we do have state-of-the-art telescopes at the millimeter, sub-millimeter wavelength kind of regime. And we saw some presentations on ALMA yesterday, which is the Atacama Large Millimeter Sub-Millimeter Array, which has been studying the system for a while. Basically, what we can do at longer wavelengths is look not only at the stars themselves, but we can also start looking at the dust and even some of the gas that is in the system. So this is just showing you that there's this tenuous ring that's been detected at these longer wavelengths, suggesting that there's something sort of like a Kuiper belt or an Oort cloud type ring structure, spheroid, whatever, around this stellar system, which is really quite interesting because we know that there's a lot of molecular and dust and atomic material that actually resides in these types of belts that has a lot of information about the history of the planet formation. And this is just sort of an artist's conception of what you might see as you enter a dusty sort of debris disk kind of region. So one of the things with looking at longer wavelengths is we can actually start revealing things that you don't necessarily see at optical wavelengths. So with the state-of-the-art Hubble Space Telescope, in optical light, we actually can't see a lot of the known universe. So if we go to longer and longer wavelengths, we actually start peering through dust and gas. And this reveals not only things like new stars that are being formed, but it also can tell us a lot about the composition, the dynamics, the physics, as well as the evolution of a given region. So it's really quite interesting to actually start pushing technology at longer wavelengths. And we know that as we do this, we can actually see more and more things. And unfortunately, or fortunately, at longer wavelengths, some of those dark traces that are obscured regions of space actually become quite bright. And that brightness is often attributed to molecular material. Now, most astronomers I talk to will tell me that, the universe is composed of hydrogen and helium, and then other metals. Well, as a chemist, I can tell you that our periodic table does not look anything like this. And we know that there's actually a lot more atomic material that's spread and dispersed throughout the universe. And actually, this atomic material actually likes to be more molecular. And if we look at certain wavelengths, we actually see the universe is filled with molecules. And actually, they're molecules that are a lot like our own that we know as far as bio or terrestrial chemistry. It's very carbon-based, based on what we've been able to measure to date. And it's actually ubiquitous. We see a lot of chemistry that resembles the organic chemistry that we know to exist here on Earth. Even though we don't necessarily have liquid water in some of these regions, we are seeing some of the same molecular tracers as well as signatures suggesting chemistry is comparable, even if not exactly the same. To study this molecular material, I can tell you what molecules exist in certain areas. And with new telescopes such as ALMA, we're now able to actually probe the molecular material of more and more diffuse regions. So when I said that we now think that there's this diffuse ring of dust around alpha Centauri, we can actually have, we're getting to the point that we have the sensitivity to see whether it's associated with molecular material, which would be huge, because if we actually sent a probe there, we would want to know what that material actually is. Next generation radio telescopes are going to be just as sensitive. And at even longer wavelengths, we now have access to things that are even far more complex than the molecules that I was just showing you, things like methanol or formaldehyde. We can actually start studying biomolecules, biotic molecules. This is really, really compelling. So a project that's been proposed is the next generation very large array. So this would be expanding the current VLA beyond New Mexico into Arizona, Mexico, and into Texas, giving us very long baselines, about 1,000 kilometers, so that we could really start probing some of these more diffuse regions of space and studying the chemistry of them. Not more importantly, we might now have the sensitivity to actually detect some of these complex biomolecules. This is just an example of some of the complex species that have been searched for. This is wrong, it's McGuire, apologies. But you can see that we have quite a number of atoms now put together, and we're getting out of this atomic regime and dust regime and into the more molecular biochemistry regime, which is really quite compelling for astrobiology and astrochemistry. But thinking about space-based telescopes, we are in the Hubble era, and it has been a huge success for astrophysics. And we are now embarking on the JWST era, or the James Webb Space Telescope. So this is the next large mission for NASA astrophysics. And it's sort of been dubbed the successor to the Hubble Space Telescope, which is sort of true because we will have sort of the same resolution on the sky, but we'll be operating at longer wavelengths and actually overlapping wavelength coverage from Hubble, which was the UV optical near infrared, with the Spitzer Space Telescope, which was more mid-infrared telescope. So on the bottom, you can see the wavelength coverage. JWST just hits the edge of the optical and goes into the mid-infrared. But it's a much larger telescope. It's a 6.5 meter diameter telescope. So the collecting area is significantly improved compared to Hubble as far as in the infrared, the near infrared. And the resolution is far superior to that of Spitzer. So we'll be able to see things and study the chemistry, dynamics, physics, as well as things like detecting exoplanets in a whole different light. As was mentioned yesterday, there was a Cycle 1 general observing program that was approved to observe Alpha Centauri. This is by Beischmann. He actually wrote a paper about doing this a number of years ago. So it's good to see that he actually was successful in acquiring time. What he's hoping to do is basically search for this and confirm the gas giant planet that's been proposed through radial velocity measurements, but also to try to measure the zodiacal dust or dust region around this planetary system. So what's shown here is an image that was acquired with Spitzer Space Telescope. And basically this is in the mid-infrared at 8 microns. This yellow square that's highlighted is showing you where the mid-infrared instrument of the James Webb Space Telescope will be searching for this planet during the time of observations next year. Looking even further, so beyond James Webb Space Telescope, the next slated observatory for NASA is the Roman Space Telescope, which is a near-infrared surveying telescope. That will have exoplanet capability detection. It does have a coronagraph on it, but it's dubbed as an infrared surveyor because it has a large field of view camera. So basically it's going to be doing a sky survey. But NASA has asked astrophysics to prioritize what the next mission will be after the Roman Space Telescope. And 4 missions were actually proposed to the Astrophysics Decadal, which should be announced or completed sometime this month, I believe. And one is a habitable exoplanet mission. One is a large UV optical infrared telescope. One is an X-ray observatory, and one is a far infrared mission. All 4 of these mission concepts will reveal complete new insight and basically rewrite the textbooks for astrophysics again, should they be selected. The habitable exoplanet mission is dedicated to studying habitable exoplanets and characterizing them. LUVOIR covers it's basically a super Hubble Space Telescope. It's a large Hubble Space Telescope that will have instrumentation and capability beyond what Hubble can currently do. The Lynx X-ray Observatory is sort of the successor to the Chandra Observatory and will offer fantastic new insight at X-ray wavelengths. And the Origin Space Telescope is a far infrared spectrometer and imaging system that will sort of be the successor of the Herschel Space Telescope or the Spectra that I showed you earlier. So one of these missions will be selected and open all kinds of doors into new questions and reveal all new insights for the local universe. If you want to think about some crazy new ideas, this is a mission concept that's being proposed. And I got permission from the team to actually talk about it a little bit with you. So this is an orbital configurable artificial star. So a lot of the observations that have been happening from ground-based telescopes require adaptive optics to have a laser guide system. So what they do is they shine a laser. This gives us a sort of a sense of what the atmosphere is doing, and we have correctable mirrors that will take into account what the atmosphere is doing based on the response from the laser. Well, sometimes your star or your object that you're trying to observe is not bright enough to do this, or you don't have access to a bright star in close proximity. So what we want to do is basically put a laser in space, so a beacon in space, so that we can do adaptive optics on almost anything, especially bright targets. So this would enable all kinds of new science, and it's really quite compelling. They've been working with the Keck Observatory to sort of have a foundation on the science and grasp what they can possibly do. But this would be accessible to basically any large telescope that had adaptive optics systems. And going even beyond, where do we go after we have something like the next large, larger than JWST? So thinking of things like space-assembled observatories is on the horizon. Whether it's astronaut-assisted assembly or automated robotic assembly, this is something that's being studied in great detail and basically will enable even larger collecting area, bigger telescopes for new discoveries in the future at various wavelengths. So just a quick summary, state-of-the-art facilities are revealing new details of the local universe, the local interstellar medium, especially the Alpha Centauri system, which has been a priority, it seems, these days. There's challenges with these new sensitivities coming on board with some of these facilities. Being so sensitive and having vast amounts of collecting area makes it really hard to observe very bright systems. So bright stars are quite challenging. So figuring out how to overcome that with the sensitivity that you still need to do things like characterization of exoplanets around a bright star. it's being overcome, but they are challenging. And next generation facilities are being planned and are going to offer new insight into the interstellar medium, Alpha Centauri, and exoplanets. So with that, thank you for your time. And I guess I will turn it over to the organizers.
Okay, thank you.
Thank you so
very
much, Stephanie. That was a great.
Go ahead, Carrie.
Oh, sure. I think up next, we have Mike Palutzak, who is going to talk to us about how to get to Alpha Centauri using fusion. Mike is the president of Princeton Satellite Systems and has worked in aerospace for a long time at GE and the Charles Stark Draper Lab. And I'm really looking forward to hearing his talk. He was also my first boss in the business. So thanks so much.
Michael, if you can hear us, please unmute yourself and start your video.
Hello?
Okay, you good to go, Michael, with sharing your slides?
Great, thank you. Let me find my slides. Can everyone see them?
Perfect.
Great. So I'm going to be talking about using fusion propulsion for Alpha Centauri missions. And the first thing we've learned about that, obviously that's the nearest star system. There are two major stars and there may be temperate zones. This is what we've all learned already. So what does fusion power provide? Well, it's propulsion to get you to Alpha Centauri. You can stop and enter the system. Power for science for payloads at Alpha Centauri. One of the big constraints on scientific satellites or scientific missions is the very small amounts of power you have when you have the destination, typically from an RTG, 250 watts. And it's amazing what scientists can do with that kind of power. And of course, power to send data back, basically data rate is proportional to power. So fusion background, and for those not that familiar, the first experiments were in the 1950s. Everybody expected it to happen really quickly, but they did not really understand the dynamics of plasmas, the instabilities. The big breakthrough came in the mid-1960s when the Soviets showed up at conferences and showed people the results from tokamaks. Nobody believed it at first, but now tokamaks have become the dominant type of machine under development in the world. There are 200 tokamaks worldwide. In the 1990s, both the tokamak fusion test reactor at the Plasma Physics Lab and the Joint European Torus produce tens of megawatts for short pulses. But this is real fusion power. It wasn't at break even, but it was a major milestone because it's the first time enormous amounts of power have been produced. Smaller fusion devices have produced little bits of power. They do get some fusion, but nothing that be considered fusion power. ITER, which is the biggest project worldwide, it's supported by all these other tokamaks, is going to produce hundreds of megawatts. And it's going to be both a physics experiment and also an engineering experiment. So there are many other configurations. We'll be talking about one today that are being developed. There are mirrors, the field reverse configuration, stellarators, Z-pinches, many other interesting ideas. And there's been a proliferation of concepts that are being tested and designed, but they're all at a much earlier stage of development than tokamaks. I want to emphasize at this point, though, that major engineering and plasma physics problems remain. Every time somebody runs a tokamak experiment, they learn new things about the plasma. So a lot of work has to be done, but good progress is being made. Our particular machine is using an advanced fuel, deuterium-helium-3. It's a different fusion reaction. I've listed them below. You get the major reaction, which produces 98.4% of the power in our system. And then there are side reactions, the deuterium-deuterium and the deuterium-tritium. Now, the way our machine works, which I'll explain a little bit more detail, is that we expect that all the tritium will depart from our area where fusion happens before it fuses. This is important because look at the neutron temperatures. For a DT machine, you're getting 14.1 MeV neutrons, which is a real challenge because they damage the wall, they damage everything. For the DD reaction, which is one of our side reactions, it's a much lower energy neutron and it makes a big difference. But the key thing is that our machine is small enough so this deuterium does not fuse. So here's the big picture cross sections. This shows the cross sections of different fusion reactions. And what we've shown here, this is, oops, I'm sorry. There we go. The TFTR temperature is shown there. It's about 50 kiloelectron volts. Nominally for DT fusion, which is shown by the purple line, you really could work it around 5 kiloelectron volts, but most modern machines can get much higher. Now for us, as you look at the cross sections for D-helium-3, which is at the very bottom, it's a blue line. You see it doesn't even begin to approach DT until you're getting up to 100 keV. Now this is important because it means we have to operate at higher temperatures. Well, okay, we showed that TFTR can do that, but what happens at higher temperatures? Well, if the electrons are that hot, we end up radiating a lot of X-rays and synchrotrons. So we must also produce power for that radiation. So we end up with a big X-ray machine to some degree. This is direct fusion drive, was invented by Sam Coe in the plasma physics lab. In a full power configuration, one that might produce a megawatt of power, we would have 7 Tesla solenoidal coils. That's basically what MRI machines or modern MRI machines produce. But we would need 20 Tesla mirror coils. Now, our concept, we use low temperature coils for those solenoidal ones. We've bought some, we've tested them. The mirror coils would require high temperature superconducting coils or hybrid coils, which is another idea we've come up with. Now, this is a driven machine, which means that we need to recycle waste energy to drive the reaction. There is no self-heating. Ideally, in a tokamak, the products of the reaction heat the reactants. So once you get it going, you only need a little bit of external heating power. All of our heating power is external. And again, as I mentioned before, we have to drive those X-rays and synchrotron too. And of course, as I mentioned, our main reaction is helium through deuterium, but we have the side reactions. Now, the nature of our machine, remember I talked about we want to get the tritium out, plus the nature of the heating. The heating is much like an induction motor, so there's a skin depth, limits us to what we think maybe 10 to 50 megawatts, probably 10 megawatts, but that's about it. Our machine has a very high beta, which is a ratio of the pressure of the plasma itself versus the pressure produced by the magnetic fields. I mean, pressure is kind of a strange term because what's happening is the particles are spiraling around the magnetic field lines, but that's the same thing. So a tokamak, it's a very low beta. Spherical tokamaks is a lot better, 0.2. We might get up to 0.8 or even close to 1. Some ideas like levitated dipoles of MIT and Dr. Teller were close to 1 or even slightly higher than 1. What we have is called an odd parity rotating magnetic field. Again, it's like an induction motor. And it switches sign, and that causes closed field, which is the difference from a mirror where the field lines open, which means the particles are more likely to stay in the machine. So these are the components, all the subsystems. There's a lot that goes into a fusion engine. We have to have the heat engine for recycling the power. The picture on the right shows you kind of the plasma configuration. And so all these are subsystems that need to be developed. One thing that is often neglected is startup. Your fusion reactor will probably need to be started up now and then, so you need a startup system for restarting. These are the subsystems, and we have a lot of support from Department of Energy and NASA for these various subsystems. Not complete, but a lot. Currently, ARPA-E Open is 2018. We're studying the plasma. A new ARPA-E program, Gamma, we're going to be looking at the heating mechanisms. This is important. Anytime somebody proposes a fusion propulsion system or any propulsion system, you want to know where is the energy going. So you can see here, we're producing the RMF only 0.32 megawatts, just for a 10 megawatt machine, is actually heating the reactants. The rest is driving Bremsstrahlung and synchrotron. And that ends up giving us 7.5 megawatts of thrust and so on. You can see all the power breakdown, it all adds up. And this is the mass breakdown. So what do we see here? Wow, radiators are gigantic. Shielding is pretty gigantic. And then the rest of it's a little bit smaller, but you can see radiators, because of the losses, which are a lot, and that's the nature of our heating engine, it's quite high and it takes up a lot of space. Here's a picture of a spacecraft. This is nominally designed for a Mars mission, but you can see the size of the radiators. And they're huge. And so you can see that's a real challenge. And there's the fuel tanks, and here's our laser communication system, which we'll talk about in a minute. So ion heating, how's it actually working? Well, we have actually two flows of ions. One, we're using a neutral beam injector, a relatively low power one, to inject the reactants into the FRC, which produces a fusion. Flowing around that, we have additional hydrogen, all ions, which actually produce the thrust that goes through a magnetic nozzle. So what happens is we get the fusion products spiral out of the FRC, so they don't react. They transfer energy via electrons to the ions in the outer layer, and that flows through the magnetic nozzle and produces thrust. And this shows you one of the limitations of our approach. It shows various power levels, and what we get is exhaust velocity. And what do you notice here? Well, the first thing is that for any given gas flow, there is a maximum thrust. So you really, at some point, you just get a cutoff, and this is the nature of the plasma physics of the flow around the edge. And then you can see the velocity data in the plot to the right. So thrust and exhaust velocity have specific limits. You can't get everything from 0 kilometers per second to thousands of kilometers per second with this particular approach. Now this slide, I've just got a lot of equations, which you can copy down. This makes you a rocket scientist, basically all the important equations, but they tell you a lot about the problem. First, power is a product of thrust and exhaust velocity. So with the given level of power, you can trade thrust against exhaust velocity, but remember the plots I showed you previously. There was limitations, at least with our concept. The mass of the system is the mass of everything else plus the power plant divided by sigma, which is our specific power, which is kilowatts per kilograms. This is really important because it limits what you can do, and we'll see in the next slide. Another interesting point, which is often missed, is that any given propulsion system carries fuel, and there's a fraction of the structural mass which is proportional to the fuel. This ultimately limits your exhaust velocity. So you can never get infinite exhaust velocity with any particular system because, of course, you have to contain the fuel. So specific power essentially drives performance. You have components. All these components must be accounted for. Our best estimate for DSD are 1 to 2 kilowatts per kilogram. However, some concepts that don't have the coils and other things are claiming 400 kilowatts per kilogram. But this ultimately is going to limit what you can do in interstellar flight. And to give you the ideas of the kind of velocities we think we can achieve, you can get maybe up to 300 kilometers per second, but go back and remember the rocket equation. That means we're not going to be able to get thousands of kilometers per second, which I'm going to show you in the next slides. As I said, Alpha Centauri missions are going to require exhaust velocities greater than 1,000 kilometers per second to get there in a reasonable time. So here's a flyby mission with plausible numbers. We have a specific power of 20 kilowatts per kilogram. Maybe and there are a lot of mechanisms for improving specific power, ranging from quantum physics to just engineering, but maybe we can get 20. So you can see that we can do a flyby in less than 400 years, which is not bad. Remember that Voyager has been operating for over 40 years, so it's 10 times Voyager, not horrible. We can actually do a mission and rendezvous in about 500 years. Now you can see the straight line trajectory on the right, and then you can see the trades between exhaust velocity, duration, and specific power. So with 1 kilowatt per kilogram, you see this line. As you can see, as we get higher and higher, we get kind of reaching a limit. So 20 kilowatts per kilogram is pretty good. You're not going to do much better than that, no matter how high sigma is. Other things in the equations factor in. But what do you do when you get there? Well, we actually came up with a procedure for entering orbit. So we pick a target planet, and then we enter the parafocal plane. We reduce velocity perpendicular to the plane. And then in our second phase, we use constant thrust to lower orbit to rendezvous with our planet. So this requires a tiny, tiny amount of fuel compared to what we needed to get there in the first place. For communications, of course, we have a lot of power. We picked these particular apertures and said, well, they could either be a laser aperture or they could be an RF, and looked at the different numbers. So with Ka band, which is a typical ComSat frequency, pretty low. Microwave, in the millimeter waves, you get a higher. And then with optical, which is why everybody wants to go to optical. It's much higher. The beam width, of course, is going to be much narrower with optical, but it's probably not a bigger problem. A precursor mission might be the solar gravitational lens mission, and this would be out around 650 to 900 AU. One of the advantages of the propulsion system we were talking about is that you could stop at that distance, and would be able to image exoplanets. It looks like you're looking at the Earth from geosynchronous orbit. So this would be rather amazing. You probably could detect if there were an advanced civilization on the planet. And of course, there are a lot of challenges. Of course, the spacecraft have to last 10 times the life of Voyager. It's amazing that Voyager is working so well this long, but 10 times is a lot further. It's not beyond the scope of engineering that's been done. Look at the pyramids, been around a long time. The locks in the canals in Panama are been operating for over 100 years. So it's possible, but it's hard. And remember, there's no maintenance. The system has to be completely autonomous. Now, most commercial satellites, like communication satellites, are completely autonomous except for station keeping. So that's not unreasonable, but you're going to have, systems that can do self-repairing and that kind of thing too, because the thing's going to fail. Interstellar drag should not be a big problem. We're really not going that fast, but something to think about. And then you say, well, what happens if we get to Alpha Centauri and somebody tries to talk to your spacecraft? We have to think about that too. We've had a lot of support from NASA and DOE. Here's the full timeline. Currently, we have ARP-E Gamma and ARP-E Open are going on. Where ARP-E Open is looking at a lot of the physics problems. ARP-E Gamma is to begin developing the power electronics for this. That's one of the subsystems. So what's the status? Well, we're doing ion heating experiments now. We're upgrading our equipment to allow us to demonstrate that we can heat ions with our approach. And the Gamma is allowing us to build a power electronic. This is for us and other fusion systems. We completed low temperature superconducting coil transient testing. That's actual hardware we brought in. So we're actually working with some of the hardware which will go into an operational machine. The next step will be, once we finish our PFRC2 experiments and we've developed these boards under Gamma, we're going to build a machine that will reach fusion relevant temperatures, not the high temperatures I showed you for an operational machine, but more like 15 keV, where we'll get some DD fusion, and that'll be very exciting. And that's it.
Thanks so much, Mike. That was a great talk. I'm really excited to hear how fusion technologies will move forward and the velocities that we can achieve with them. I think up next, I know you mentioned using laser communications, and we have from NASA JPL, Tom Roberts, who's going to talk to us about the state of the art in deep space optical communications. Tom has a background in optics from the University of Arizona and the University of Alabama at Huntsville. And thanks so much for joining us, Tom, to tell us about what you're working on right now to do deep space optical communications in the solar system.
Good morning. Let me get set up here. Good morning. I'm Tom Roberts, as they mentioned, from the Jet Propulsion Laboratory in California. Before I begin, I'd like to just recognize my co-author and friend, Dr. Abhijit Biswas, who's also in the optical communications group at the Jet Propulsion Laboratory. So let's go ahead and get right into it. By way of introduction, first, before we get started, I'd just like to mention that it took a little while once I got into the telecom community, but almost everything is measured instead of in actual numbers in decibels or dB, which is about 10 times the log base 10 of the number we're measuring. And we use that for almost everything. For example, lasers are in dB watts or dB milliwatts. Irradiance levels are in dB watts per square meter. Our funding levels in dB dollars, well, we don't take it that far usually, but just about everything else is. So one of the things that I just wanted to get across was we've come a long way in the last couple of decades toward the realization of optical communications, and we have a lot further to go, but we've got ideas about how to get there, and I'm planning to discuss some of those in the later half of this talk. So one of the things that we usually do, and here's where the dB come in again, and that is we do a difficulty measurement or our difficulty. Our way of discussing how difficult the problem to be solved is. And usually we use the product of the data rate, usually in megabits per second, times the distance. And it's convenient in this talk in particular to use AU as distance, astronomical units. One of the early progenitors of this was the lunar laser communications demonstration, which was a project in 2013, where we transmitted 622 megabits per second from an orbiting spacecraft around the moon back to Earth. So that distance, for example, is 0.0027 AU, or about 2.7 times 10 to the minus 3 AU. In going to the most recent state of the art, which is the Deep Space Optical Communications Project, which I'll get to in a moment, or DSOC as we call it, we're talking about going up to about 2 megabits per second from a distance of 2 AU. Actually, we'll probably go a little further than that. So if we take that metric that we mentioned before, megabits per second times the square root times the AU squared, you see we get about a 32 dB, or a little over 1,000 times more difficulty in achieving our data rates at that distance than we are than we experienced about 8 years ago in the LLCD project. Since then, we've also gotten a spacecraft, optical communication system on board the ISS, which was the Opals project over here on the left, as you see, and that communicated at 50 megabits per second from a tiny little aperture down to our ground station at the Optical Communications Telescope Laboratory, close to Pasadena, California. And now we're going to be launching in the next couple of months the Laser Communications Relay Demonstration, or LCRD spacecraft. That's going up from the Cape in about, as I mentioned, 2 months on June 23rd. And it's supposed to relay data from a geosynchronous spacecraft from one ground station up to the spacecraft, and then through a bent pipe down to the other ground station at over a gigabit per second. And it should be able to do that pretty much anytime, day or night, under almost all conditions. Of course, thick clouds we can't go through, but most other conditions we can handle. So now in going to the Deep Space Optical Communications Project, as I mentioned, we've got 32 dB more difficult problem than we had under the Lunar Laser Communications Demonstration Project. And now that we're going to Alpha Centauri, it looks like we've got about a 72 dB or 40 dB more, a 10,000 times more difficult problem in communicating back at even just 1 bit per second. So let's get into what the DSOC spacecraft is and what it'll be doing. The dance starts with a 5 kilowatt transmitter that's transmitted from our ground laser transmitter at the Optical Communications Telescope Laboratory up to the spacecraft. On board the Psyche spacecraft, which is going out to the Psyche asteroid, we've got our communication system, which has a 22 centimeter unobscured aperture, which reflects the light down into a box, which is effectively light tight, other than for the opening of that small pinhole that it focuses through. And that gives us the ability to point very close to the sun and operate under pretty much all conditions that we'd be dealing with. The whole system is designed out of silicon carbide, which has a very nice property of being very athermal and yet at the same time highly thermally conductive. So it allows us to operate under a wide variety of conditions. And the whole system, in order to reduce the amount of jitter from the spacecraft, the whole system is floated during operations electromagnetically using these electromagnetic adjusters that adjust the fine pointing of the space terminal, as well as preventing jitter from getting to the space terminal. That then communicates with a 4-watt laser back down to the 5-meter telescope at Palomar Mountain, the Venerable Hale telescope. So we've run the numbers on this. It looks doable. We're launching next year, and looking forward to what happens when we get out there into deep space in particular. Now, in order to do this, we've got several things to deal with. One is the downlink equation, which is in general not particularly in our favor in going further and further out the way we are. As an example, the LLCD beacon and the downlink laser had irradiances in terms of watts per square meter in these ranges, around a nanowatt per square meter at the Earth. And yet, what DSOC is required to do is go even further out, down to several AU here, and so that we get significantly less irradiance at the far field for the spacecraft for the flight terminal to lock onto, and then to send back down to the ground station. So we pulled a few tricks out of our sleeve. We've done some optimization of things. One of the things is the laser transmit power has been increased by about an order of magnitude. This was a technology development project that has worked out nicely, and we've got a high peak to average power laser transmitter that's transmitting 4 watts. Like I say, it's about an order of magnitude more absolute power than we've been using in the past. The transmitter efficiency is also designed in order, as I mentioned, it was an off-axis paraboloid, and that allows us to get a couple more dB out of it by eliminating that obscuration that most on-axis telescopes have. Now, of course, when you start narrowing your beam to get increased gain, you get beam pointing control problems. So we had to develop this other piece of new technology, both the spacecraft low bandwidth pointing control and those struts that I mentioned that electromagnetically levitate the spacecraft so that it keeps it pointed where we want to without transmitting jitter from the remainder of the spacecraft. In addition, one of the knobs that we have to tweak is the aperture of both the space transmitter as well as the ground receiver. And so that's why we're using the 5-meter Hale telescope on Palomar Mountain as our ground receiver, and why we've increased from about 10 centimeters to about 22 centimeters, the transmitter gain of, well, the transmit diameter of the flight terminal. And then finally, the receive efficiency has been improved by improving the detection efficiency of our low dark noise photon counting detectors. Now, that's not all that we can do. There's also new from the Consultative Committee for Space Data Systems, the CCSDS. They have a standard for high photon efficiency signaling. And basically that's what we go to. We go to something called pulse position modulation, which allows us to send multiple bits of data within a single pulse. Now we have to actually trade a bit of bandwidth, in fact, quite a bit of bandwidth sometimes in order to do that, but that still allows us to get an intense enough pulse that it can be detected among the noise down at the ground station. We have forward error correcting codes. We have interleaving, which allows us to avoid deep fades and actually disperses the effects of those deep fades among the remainder of the code words that can be then error corrected. Then finally, we have a variable data rate. We can allow it to go to lower data rates to improve the photon efficiency of the system so that when we get out into deeper space, we still can maintain the link, albeit with a much lower data rate. So we play some of the same tricks on the uplink, but in particular, one of the things is the up-down counting that's used for background subtraction. And we use actually a very low data rate, about 1.6 kilobits per second for the uplink. Of course, that data is not nearly as important as what we want to get down. So here are some of the components of the hardware and some of the limitations that we've run into. Over on the right here, you'll see the optical transceiver assembly, or the OTA. This uses that, as I mentioned, 22 centimeter silicon carbide aperture. The remainder of the system is designed to be out of silicon carbide so that it stays effectively isotropic expansion and contraction of the system. The remainder of the system is encased in a box where it can be light tight, so we don't, or effectively light tight, so that we don't have the significant amount of background radiation from the sun transmitted into the system to spoil our pointing. In addition, we've developed a new laser transmitter assembly. As I mentioned, it's about 4-watt average power, and it's capable of the high peak power ratios of about 160 to 1. Now, one of the things that we've designed the system for is to be able to operate pretty much anywhere in the inner solar system, out to about perhaps Saturn, if we increase the size of the primary mirror. But at the same time, we wanted to test it under all conditions, but because we're using the Hale telescope, which is a very highly used astronomical instrument, they didn't want us to get that pointed that close to the sun. So we're only doing nighttime links, even though the system should be capable of handling daytime operations as well. For the sake of the telescope, we're limiting to nighttime. And in addition, DSOC doesn't carry any redundancy. So there are a number of single point failures on the system, and we have to simply accept that for the conditions that we're running in. And then finally, we had a ranging and high data rate uplink that we wanted to do. But because this was a development project for the ground-based laser system, which wasn't really along the lines of what we actually intended to do, we've had to descope those. So where are we going from here? One of the things that we do is we like to use these large apertures. And as I mentioned before, aperture is your friend. If you want to get better collection area, then you need to use a large aperture. And one of the approaches we've taken to save costs is to actually tile the inside of one of our 34-meter radio dishes with optical segments that then get combined back behind the RF subreflector in a telescope system where we would keep our high photon efficiency detectors. In addition, we've looked out beyond Mars at this point, and going to the outer planets, we've got an idea that we can switch over to LWIR, or long wave infrared radiation, as our beacon, because as we get further out, the Earth becomes more and more like a point source, which allows us then to track it. But because the ratio of radiance from the Earth and the long wave infrared relative to the sun is more in our favor, that's why we go to long wave infrared. Now that drives us down to having to operate at lower and lower temperatures, which we can do pretty easily as we get further out in the solar system. We've also looked at optical communications from Uranus and Neptune, and we've gotten from these distances of about 17 to 21 AU and 28 to 31 to 32 AU for Neptune. We expect to be able to get under nighttime conditions several megabits per second. Here as not quite as many megabits per second, actually very few, we're on the order of about a megabit per second at Neptune ranges, but still it's doable with current technology. It does assume a 5-meter Hale telescope again, and we could do better than that if we went up to an 11.8 meter collector, such as the Large Binocular Telescope of Mount Graham in Arizona. So we'd also require some technology development in the lasers to be able to get even higher peak powers and higher average powers so that we can blast our way through those long distances that we have to deal with out to about 250 astronomical units. And we projected that the link performance would be sufficient to do that under these conditions, assuming we had about 100 kilowatt peak power laser. And that still is operating with about a 5 dB of link margin on that, which we really want to keep under these kinds of conditions so that we're sure that we get something back. So now, one other thing I'd like to point out is that 250 AU is really only about 0.1% of the distance we're talking about. So we still have a number of orders of magnitude or tens of dB to overcome with this. But I'm sure with increased technology development and with continuous funding in dB dollars, that throughout the future, we'll be able to get there at some point. So thank you very much. It's been a pleasure talking with you, and we wish you the best.
Thanks so much, Tom. Great talk. I think Harry and I will be going through the very extensive questions. If you do have questions, please go ahead and put them in the Q&A. Try to include the speaker name that you're directing them to. And then I think we'll try to cycle through these, right, Harry?
Yeah, that's right. Yeah, I think why don't we, before we go to our panelists, there were a number of questions for George, and maybe I'll start with the most philosophical or ontological, shall we say, which is from Grover Schwartzlander asking, assuming we have a sobering window of opportunity for humans to terraform an exoplanet and prepare it for a migration, do you think that humanity will have the luxury or sensibility to take baby steps, or should we simply disperse DNA from the Earth at great haste? Maybe we don't have enough time to waste, actually.
Well, you know, I think that ideally, we would be able to study it extensively before we contaminate it in any way to know if there's anything there. And whether or not we're terraforming, we could affect the entire planet unintentionally. I think that's already happening on the places that we're visiting, because the planetary protection protocols only have some lower threshold, which is not zero, which is reasonable, but it results in a high probability of contamination of a replicating species. So I think at some point the benefits will be perceived as outweighing the risks, or the contamination that already exists will be considered dominant. I'm glad I'm not the only one making that decision. It's something that I think would take a great deal of discussion.
Okay, and then maybe a little closer to home, another question for you, George, about whether any of the schemes that you, sort of capsids that you imagine forming to transport biomass would these be able to survive, for example, in the upper atmospheres of Venus, which is another regime for potentially hosting life that's been discussed at this conference?
They could probably survive. Whether they could replicate, it's a very low concentration of water, and it's not clear whether there's sufficient gradients in potential metabolites for inorganic. But it's certainly within range for doing photosynthesis. So I don't know. I mean, it's an interesting question. I'd love to have more in-depth discussion about it. Certainly, it's possible. It's close enough that we can launch a conventional probe, in which case the upper atmosphere is, around 50 kilometers or so, is so close to our gravity and atmospheric pressure and temperature that we could populate it in a flotation mode.
And by the way, I'll selfishly interject my own question for you here, which is I was fascinated by the laminate structures on the carapaces of the beetles that you showed that have very high reflectivity. This, of course, looks like maybe a biomimetic light sail material or perhaps a reflector for optics. I was wondering, a couple of questions. One is the residual part that's not reflectivity, is it going into absorbance or is it transmitted light? And then finally, why on earth would the beetle care to develop a structure that has a reflectivity of 80% or 90%?
All those are great questions. Probably a lot of absorption is, a lot, meaning the 9% not reflected is absorption. I don't know the exact frequency, fraction that would be transmitted as well. Why it wants it, well, many of these things are display modes for part of reproduction of mate attraction. I don't know the exact answer there's quite a number of insects beyond these beetles that do this as well. Is there another question? I think it was.
I think that was mainly it, and I'll just make a comment about your. You weighed in with the idea of perhaps making a glass-based laser system and using in situ resources, and to me that it seems that if it were possible to cast the materials, it seems like a reasonable concept. For example, making photovoltaic devices from the lunar regolith has already been proposed as an energy harvesting approach on the moon. So it doesn't take too much imagination to go from that one to another. I would think the big challenges would be in arranging the laser cavity and so forth to accommodate the gain medium. But that seems like a very interesting idea to exploit.
Thanks. Yeah.
Yeah.
My favorite question in here was for Dr. Milam. So it's definitely, and I like this question because it could leverage the laser guide star concept. As you know, we're big developers and proponents of that over here. But is there any hope or progress for in-space formation flying synthetic aperture type optical telescopes, say with a few kilometer baseline, like you were describing, so the next generation arrays, but can we do that in space for direct imaging of exoplanet surface features? And, comes to mind, like, could you use that same remote guide star to sync up apertures as well in space?
Yeah, I definitely think so. So we've already demonstrated successful formation flying at standard distances. So like MMX, for example, was a heliospheric mission that did formation flying. And so we know that we can do this with the spacecraft platforms. So being able to extend this into observatories or telescopes, I think would be a very compelling thing to do. The challenge is accuracy. So getting the accuracy and position, especially when you're at optical wavelengths, is really quite challenging. We already know this just by building larger mirrors, for example. Getting surface accuracy is something that you have to achieve in order to get the, the resolution and the image quality that you really want. So I think if we could get the positional accuracy down, that would be the first step. I know that this has already been studied as far as not necessarily formation flying, but just having sort of a boom-like structure with two primary mirrors on the boom. So then you have a control of the distance, for example. And this has been studied for like far infrared wavelengths. So I think pushing that to the optical is going to be challenging, as I said, but I think it is definitely feasible. And the formation flying is going to be even more challenging at the shorter wavelengths, but maybe something to start with would be longer wavelengths. There's even been discussion about having a space-based radio telescope that we could couple to things like ALMA or the NGVLA to give you this super extended baseline. So you can imagine the whole imaging black holes going to the next level now. You don't have the Earth now as your baseline. You have something like the moon or even an orbiting spacecraft. So I think that's really quite compelling. And yes, Carrie, I think having the laser guide star system, there's been discussion with that particular system of having multiple laser guide stars so that you can have either different types of radiation as a laser, so different wavelength coverage, so it's more versatile across various telescopes, expanding even say into the infrared or into the millimeter, submillimeter regime. Or covering more space. So if you wanted to do sort of a more extended imaging, you would need multiple guide stars. And I think that would be something that's very compelling, and having that type of flight would be definitely something to look into.
Or different colors. And I'm seeing, I feel like this is something that our entire panel can comment on in one way or the other. I'm guessing Tom has lots of comments on this on the optical side of things, and Michael probably has lots of comments on this from attitude control and formation flying, and Archer probably has a lot of comments on materials and precision. So I don't know if we want to just allow each of you, maybe Tom, Mike, and Archer, to also respond to that question a little bit, because I think it's one that really can pull us all together.
Yeah, I'll go ahead and go with that. And that is, if you're going to have, say, a distant or perhaps even a lunar-based RF system you're trying to link up, you'll need optical communications to transmit the information back and forth and keep things aligned. So I know where you can get one of those. Let me know.
All right, and Mike? Oh, Mike, I think you're still on mute.
Yeah, I mean, the attitude control is challenging, but you're going to end up, as the speakers mentioned, with a multi-stage system. So you're going to have your basic pointing control of your spacecraft, which can be quite tight, but then you got to shelter the optical system from your disturbances on the spacecraft. Then, of course, if you're doing some sort of synthetic aperture, you have to know your relative positions. So you actually have to know where your receivers are on your spacecraft very accurately. There was an attempt to do this with TechSat 21. It was a radar system, and it simply was beyond the station keeping technology, maybe 10, 15 years ago.
Cool. And then what about on materials and the surfaces?
So one of the challenges that's out there is actually the cost of these telescopes to put them in space, and JWST is a great example. But what we're seeing in recent maybe 10 years is like big revolution going in optical field is flat optics, like very thin systems that are very agile and they can form imaging, and they're tunable. So we can envision multiple apertures with these systems that quite close to the light sail. They're a little bit different shape that can be deployed, and they can form this, several telescopes or formation flying of the telescopes. and they can be also like, you know, tunable in the sense that to control the wavefront, to control the precision.
I mean, one thing I'd like to mention is that Gravity Probe B had an extremely low jitter point and control system. And so that sort of is what you can achieve if you really try.
So I'll just chime in here and note and reiterate a point that was made in the chat by Wesley Green, who's working on the photon engine project for the Starshot program, that indeed a orbiting beacon similar to Orcus that Stephanie discussed is something that's anticipated for the Starshot program to compensate for example, atmospheric refractive index fluctuations that you'd have to compensate for a ground-based laser system sitting on a mountaintop pointing at a light sail in space. So the guide star is a common need and very leveraging from this NASA program for Starshot's ambitions.
Yep, I agree. I believe we have a poll. Harry, I don't know if you want to announce it or you'd like me to for our participants.
Yeah, let's see. Maybe we can have our Jamie and the. Okay, here comes the session 3 poll. Okay, so the questions are, and you get to choose. How would you harness energy to sail a spacecraft from Earth to the next star system? And you have a choice between photons and fusion. So that's number 1. Number 2 would be the question, should the journey to Alpha Centauri be a flyby, or should we build systems that can decelerate and be captured? In other words, hit the brakes or buzz the tower, fly by and itinerant view for a short period of time and sail on by. And then the third question is about sending data back. Should we leave a trail of network communication relay beacons or construct a large ground-based transmitter or receiver facility on the Earth and do it all in one shot? So 2 choices. Can you hear me now? Networked relay beacon or beam me up directly all the way from the Earth in a transceiver format. So go ahead and begin entering, and then we'll discuss the outcome of the polls a little later on in the discussion. Now I wanted to actually move back. There's a question here that has gotten quite a lot of attention and was brought up several times, which has to do with, in fact, starting yesterday with James Cameron, about the thermal stability of materials. And the question, Artur, I think that's lurking in everyone's mind with a laser-pushed sail at the power densities that are anticipated, is the sail just going to burn up, or do we have thermal models and thermal and data for materials that suggest that the problem is manageable?
Yes, I didn't mention it in detail in my talk, but generally speaking, what we are seeing is that indeed we can manage the thermal loads expected for the Starshot power levels. So it's 100 gigawatts of power that is input on about 10 meters square, about 10 meters square, a little bit less, a little bit larger than that sail. So if you do the math correctly, for low absorbance materials, like, you know, very low absorbance materials, and there are several of them. Like, for example, the molybdenum disulfide is one of the candidates that I showed in my slides. Another option is silicon nitride and also silicon. So several material candidates that are out there. So they are quite low in absorbing the power. And that means that all of this power is pretty much reflected in very small fraction, just, you know, 0.001% is absorbed in there. And now you can engineer the emissivity to emit the light. So what we see is that we can keep the sail material less, the temperature with less than the melting point. And for the missions that I kind of described, outlined a little bit for, you know, sort of precursor missions, the prototype missions, where we would go for the interplanetary travel rather than for, you know, aiming to the Alpha Centauri system, for much lower power levels, like, for example, 10 megawatts or 1 megawatt, then the sail temperature is not a problem. We can keep it much below the 500 Kelvin, I mean, the room temperature most likely. So I would mention here is actually when I was seeing George's talk, I was thinking about the power density there. So what would happen is that when you have very small probes, like nanogram probes, you don't have much area to radiate the heat away. So the thermal loading of those type of systems with propulsion might be a challenge, although doable.
You also don't need many photons,
That's right.
so it kind of cancels out.
All right, are we ready to go through another question? I thought one was directed to Tom that was pretty funny, which was, what about those daytime DSOC tests on the optical comm? You can try to do comms, but not point directly towards the sun. You can point kind of away from the sun and still try to make a contact. Do you want to talk a little bit about the kind of, in addition to, the light years of delay in getting data, can we operate while we're in the sunlight, or do we have to wait for the eclipse side to be facing alpha sun?
Well, for DSOC in particular, really out of deference to the astronomers and to make sure that we don't upset the thermal equilibrium of the telescope, we're really just targeting nighttime. However, the DSOC flight terminal itself has been designed such that it could operate at any particular point. And that becomes more and more important the further out in the solar system you go. As you go further out, Earth is always close to the sun. So we have to be able to handle that on the flight side. Now on the ground side, that's a different matter. We can possibly put different, well, really when discussing, I haven't given much thought to this, but when discussing planetary systems, the planet is often close to the sun or on the other side of the sun. As I mentioned, Mars is usually about 60 to 70% of the time in the daytime sky. So we have to be able to operate that, and that's one of the prime elements of our ongoing effort. And in fact, that is one of the drivers for actually putting together this RF optical hybrid telescope that I described, because it does operate any time of day, and we're talking about operating down to within 3 degrees of the sun. So that is not undoable. It's certainly a very potential. We have a lot of potential to achieve that. I'd just say that, but it's going to take some investment to do so.
Thanks, Tom. Harry, did you want to ask the question on the power limits on the light sail by Lee?
Let's see. I think we talked a little bit about that with Archer.
We did.
Yeah. I actually wanted to ask Michael a question, which has to do, Michael talked about specific power and the impulse and the total power of a fusion system. But I was wondering if you could give us sort of an impression of this, the total scale of the size of the power system in the spacecraft for an envisioned fusion drive. Is this something that the scale drives you to thinking about very large scale spacecraft, or can we envision very small scale spacecraft? And so we could proliferate spacecraft traveling in many directions and many missions.
I mean, that's a really good point. The example, typically we're looking at a lot of interplanetary missions where you're moving, say, 1,000 kilograms. And that required, you're able to do a Pluto mission, for example, with an orbiter with a 1,000 kilogram payload with a 1 megawatt system. So yeah, I think that's a good point. You probably, and this is in terms of actually getting anything to Alpha Centauri, you probably want to go with a bunch of smaller spacecraft. It's sort of interesting because if you ran into interstellar matter, which maybe even this 50 micron size, that's like hitting a 50 caliber bullet. So that's another reason for you want a lot of redundancy. But yeah, the thing about our system is that it, in theory, if all the plasma physics works as we expect, 1 megawatt systems are quite reasonable. Other fusion concepts really start around 200 megawatts and would, obviously a much bigger payload.
There is an interesting question, and I know that there are folks who are interested in this. The difference between a solar sail and a laser-propelled sail in both capabilities and materials and sources. And I think, getting farther and farther away from the sun is one of the things we're doing here. But then we'll get closer to Alpha Sun on the other side. So can we combine both approaches, or how are they very different from each other? And I think those are questions that maybe Arthur and Harry can guide us through.
Sure, I'll be happy to start that one, and Harry can continue here. So the system level difference, like before we jump into the materials, is that laser sailing requires a large laser. And for missions to Alpha Centauri, we're talking, in the context of the Breakthrough Starshot, we're talking about 1 gram class payloads. Maybe a little bit more if you go to nearby distances like outer planes and so on. Solar sailing does not require laser arrays, so it's much kind of simpler architecture and cheaper in that sense, right? So you just launch a sail that you can build in a CubeSat format, and we're doing that already now. The problem with the solar sails, the limitation with the solar sails, as I showed in my slides, is the maximum velocity that we can get is about 60 astronomical units per year, 0.1% of the speed of light. For the laser sailing, we can get to 20% of speed of light, maybe more if we put enough power in there. So it's like, kind of unlimited in that sense. From the materials point of view, these two approaches, they share the same problems, that we need to manage the heat and reflect light efficiently. But because of the different wavelengths and different limitations on the wavelengths, we have different materials problems. So in one case, we need really broadband reflectors that are indivisible for, especially from UV, because the UV is absorbing quite a lot for the solar sails. And in the laser sailing, we just need to carry in the laser domain, which is around 1200 nanometers wavelength. It's a little bit of window there. So challenge is similar in terms of kind of balancing the absorption and the emission of radiation and making it reflective, but the material itself is going to be different for the laser sail and for the solar sail itself.
Yeah, I'll just note that also for the laser sail, there's you should really view this as a coupling of the laser and the sail as a complete system. And given that the laser is a phased array aperture, that gives quite a lot of freedom and flexibility to define the beam profile throughout the entire propulsion impulse. So that's a flexibility that you don't have with the sun, where the sun is an isotropic blackbody radiator. And the light sail is at a specific laser wavelength, so we can design the sail in a way that's tailored to the properties of the laser, which is an interesting opportunity. So had another question we wanted to pose for Stephanie, which is the relative, in the chat here, which is the relative velocity of the local interstellar medium with respect to the local stellar standard of rest. I guess maybe we could generalize that to tell us a little bit about the properties of the interstellar medium, its temperature, the velocity, inhomogeneity, and so forth, things that we would want to worry about if we were transiting through it.
So to directly answer the question, it's about 25 kilometers per second. Okay. I can check that box off. I answered the question. But in general, as I presented, it's diffuse, where maybe a molecule per cubic inch. Or meter. Excuse me. We're not really worried about an extensive amount of material that we're going to have to get through. But as was mentioned, there is still dust. We know there's dust, and even if there isn't a concentration of dust consistently, we have to go through a handful of ring-like systems regardless. So the Kuiper belt versus the Oort cloud, or any of these other potential dust-like features, Zodi-like things in the Alpha Centauri system. So I think that dust is currently we're working on characterizing what that dust may be comprised of, and as far as the size and distribution, we know in alpha Centauri it's pretty diffuse, but it was detectable at millimeter wavelengths, which suggests you have something approximately millimeter sized grains on some level. Whereas as we get into the JWST era, I think we'll start finding the micron size grains and maybe some of that dispersed dust that's more like the ZODI. So I think that we will know the answer to this sometime in the next 2 years with the successful launch of JWST and now a successful proposal to try to measure this. So I think we're working on characterizing what that looks like as far as the alpha Centauri system goes. The outer solar system, we have yet to detect the Oort cloud. We are sort of at the brink of understanding the size range of the Kuiper belt as far as meter scale and downward. JWST is going to open up a new realm of detectability for smaller bodies in the outer solar system, but they are few and far between. We know that from New Horizons, for example. Just finding another object to try to get to after the Pluto flyby or the more recent Kuiper belt has been quite a challenge, because there is a lot of distance and there's a lot of space in between these objects and bodies. So as much as we want it to be asteroid belt like for some science cases, it is pretty diffuse. And I think the larger bodies are less of a concern. I think the bigger issue is going to be things like the micron sized dust, which as was already mentioned, when you're traveling at these speeds is going to be quite detrimental to any spacecraft. So.
Yeah, so about those self-healing materials. I think that's where we are, right, Stephanie? I don't know if
especially with JWST, right?
Right. Well, yeah.
So that's an exciting time, because that information will become available on a timescale that's extremely well timed for the development of light sails and lasers for the Starshot mission. So that's very opportune.
And I think the even just the sun shield on JWST is going to reveal a lot of information about durability, and even though it's much closer to Earth, I think we'll learn a lot.
So we do have some. I know that there's been a lot of focus on lasers and optical communication and propagation here, but there's definitely questions out there about, well, why not radio? Why are we so laser focused here? What kind of power trades are we subjecting ourselves to if we did decide to do radio?
Well, I can jump in here and
Tom, can you play devil's advocate for a couple seconds?
Sure. Radio is great in a lot of different ways. One of the things that it's not very good at is you need a huge array in order to try to focus it down. So when radio works, it has the advantage of not being so dependent on a low jitter system, but at the same time, it is not very efficient at concentrate. It's very inefficient, let's say, at concentrating the signal and achieving the gain that optical can achieve. So that's the primary reason.
Together with that, like some small kind of addition here, absolutely right. So we need very large array in there and so on. But also, if we look into the military grade spacecraft at the geostationary orbit, not even Alpha Centauri, the radio sources there, they use huge, basically vacuum tube transmitters. And so I don't really know how to integrate a huge vacuum tube transmitter with the 1 gram payload that would gonna go to Alpha Centauri. At the same time, lasers, we see the pathway that can do it. And it's not there, but it's kind of foreseeable pathway.
Well, I don't know. I mean, even Mike had lasers on his fusion reactor, not radio. So I don't know if Mike wants to comment as well.
Well, it's the same
you could
thing.
maybe carry a radio, right, Mike?
Yeah, you're always going to have a radio, at least for near Earth communication, because just because, you know, everybody has a Omni on their spacecraft, or should. But, you know, in terms of data rate, if you're going to get your money's worth out of an Alpha Centauri mission, you know, it takes you 500 years to get there. You're in orbit around a planet. You're going to want the data rates to be as high as possible. So yes, you can get data back using millimeter wave or K band or whatever, but it makes sense to go with optical. So you're going to solve, if you can solve the problems of building a 500-year interstellar spacecraft, I think you can solve the problems of laser communication.
So I had a question for, I guess, everyone and Stephanie, but is there anything wrong with the idea of trying to chase down a comet or interstellar object and just hop on and you know, you take enough energy to get there and intercept with it and then take it for the rest of the ride?
So intercepting an interstellar object is a topic of extreme interest, especially right now. The planetary science decadal is underway, and I'm on the small bodies panel, so you can imagine how much this has come up. So this is something that's actually been proposed through the ESA mission, not necessarily to ride it, but to actually encounter one, do some in situ science. So this is a mission called Comet Interceptor. So basically they're going to sit and wait for an interstellar object to come by, and then they're going to go to it. And it's a multi-spacecraft mission, and they are going to do some close proxops type science in situ, and then some other flyby stuff. It is quite challenging. There's a lot of issue that comes to planning something like an interstellar object mission. Mostly it's just we don't know where they are. We don't know. And usually when we discover them, we have, you know, a very short period of time before they're closest to the sun or approachable at all from Earth. And so do you have a spacecraft sitting, waiting for the right opportunity where it's constantly being degraded, you're burning power, you're burning fuel, whatever you need just to sit there and wait? Do you have something sitting on the ground, basically in a rocket waiting to launch for the right opportunity, and hope that you have everything ready for it? These are all the key questions for the now. Let's think about decades ahead. Yes, I think it is something that's going to be achievable, especially if we have sort of, you know, a lunar base where we can just have spacecraft sort of sitting, waiting at the ready. But then, yeah, why not hitch a ride? We found with Rosetta, it's very easy just to stay in orbit around some of these bodies. And we think that they might be large enough that it should be easy to stay. And then communication, again, becomes the issue. So there are challenges, but it's definitely very compelling. And as somebody that studies interstellar objects, I can tell you, I would definitely like to see one.
I mean, we have chased down and taken samples from comets and then crashed them back into Earth before. So, you know, I figure we can handle this. But Arthur, you look like you also wanted to jump in maybe a little bit on this. So
yeah, sure. So we looked partially into that. So the fact that they are interstellar already tells us that they move faster than any object that we have in our solar system itself, right? And then they actually, like the heliocentric speed of the interstellar objects like Barisa, for example, I think it's about at least two times faster than the Voyager 1. So that tells us that with conventional spacecraft, conventional rockets, we can't really do that. Maybe if we position them smartly enough, then we can do it. And that's where the light sailing or some other means like nuclear fusion or whatever it is, that can help intercept, first of all, the interstellar objects. But then also the beauty of interstellar objects is that they have to provide like a lot of mass and a lot of space to basically build things on top of that, right, and ride it. The downside of the interstellar object is that, you know, again, speed. Although it's fast, it's not fast enough to get to the interstellar basically star.
You know, we anticipate that if our nuclear fusion technology is successful, you'll have a number of these spacecraft in Earth orbit about to depart on many missions, and one could be an asteroid, an interstellar object intercept. In fact, we plotted a trajectory for that, and I can send it to people if they'd like to see it. For that reason, the other thing you'd like to do with a fusion engine is be able to intercept asteroids that are going to hit the Earth. So there's sort of a generic class of missions requiring you to intercept things moving really quickly.
I'm glad you're thinking about saving the Earth. I appreciate that. I think it's the only one we've got. Anyway, Harry, did you have other questions you wanted to direct?
I thought I'd bring it back to Tom to maybe say a little bit about what are the lessons learned from DSOC and that are potentially translatable to thinking about communications on the interstellar scale. You talked about data rate at sort of a bit per second. What about some other issues like signal to noise of the signal? Would you use the same pulse phase modulation scheme? Is pointing an issue, for example? Setting aside the issue of finding, say, Proxima B relative to Alpha Centauri, simply pointing at Alpha Centauri and keeping well pointed on the spacecraft nearby there.
Yeah, that's a good point. One thing that I didn't mention that we have to deal with, that radio frequently doesn't have to deal with, is a point ahead angle, because radio waves are so broad in general in their transmission. They don't usually worry so much about it as we do. We're trying to hit the point, get the light there to the point where the Earth will be when the light gets there. So we have to point ahead, and that's twice the speed of light divided by the crossing velocity. I'm sorry, twice the crossing velocity divided by the speed of light. So we're not actually pointing where our beacon is coming from. We're pointing ahead to where that beacon is going to be when the light that we're sending out gets there. So that's one thing that we have to worry about. And I'm not sure what the cross velocity speeds are of Alpha Centauri. So that's something that we need to look at. Another thing is the pointing does become more of a problem because of this huge gain that we're counting on for getting the signal back there. We have to have our beam extremely narrow. And when you get extremely narrow, then even a slight perturbation away or mispoint to it would be hugely detrimental. So we have to be very careful about that. And the third thing is that because it's a 8.5 year round trip light time, we wouldn't at all know what we couldn't use feedback from the Earth to say, oh, you're pointed off a little bit, you need to repoint. So those are all problems that we need to deal with. There's a limitation to the amount of pulse position modulation, the Emory problem that I mentioned, because every time we want one additional bit to be included in our pulse train, that requires a lengthening of the pulse of the separation of the pulses by about a factor of 2. So we can play those games for a while, but it eventually becomes a losing game. We need to increase the power in that case because we can't increase the instantaneous power. But very good questions. Thank you.
I have one, and this is on behalf of one of my graduate students. A lot of them work in LaserCom, but one of them is working very hard on his PhD to send the first, he's trying to send the first closed miniature ecosystem on a CubeSat. And I was wondering if I could pose this one to George, if you could design a series of closed ecosystems to try to launch into space for experimentation and first steps towards using biological organisms to, kind of carry forward on this path of exploration. How would you structure that, and what would you think about?
So there are quite a few experiments on closed ecosystems going back at least 6 decades, none including human beings, but that's not really the topic here. All human systems are open in some sense. I think what's interesting here is preparing the ecosystem for a variety of possible environments. So it may not be as simple as one photosynthetic organism. It may be that there is an actual ecosystem required for even the simplest of goals, but unknown environments.
Yeah, so he's working on, I don't know if you've seen those ecospheres with the brine shrimp in them. So building a CubeSat that would thermally control that and keep it from shattering, and use the right instrumentation to monitor the state of the ecosphere and the health of the systems within it. It just is a fun concept to try to grow from there, if that's not a pun on words.
No, those brine strip last for years. The systems that are immortal are the ones that have microbial systems or enough photosynthesis to large enough size so the brine strip can procreate, which they don't typically, at least in the commercial versions.
Would you include light sources to try to simulate photosynthesis as they're traveling through interstellar space, or just try to find something that would hibernate in between star departure and arrivals?
Well, I mean, hibernation is easy. A number of these organisms do quite well at 3 degrees Kelvin. So the main problem is that if the journey is a long one, they will suffer a lot of radiation damage. So it'll be integrated over time where there's no repair going on. So the organisms I listed that could tolerate up to 15,000 grays were doing so with active repair processes. So that's a nuance that one would have to take into account. Or you could keep them just high enough temperature or intermittent temperature so they can repair and then go back to sleep.
So George, I have a question for you too, which builds on an observation that came out of a discussion I once had with Avi Loeb, your colleague, who said we should not only build light sails, we should be looking out into the sky for the flashes of light sails being launched at us, towards us. So the question in the chat came in, should we similarly be looking for biosignatures of nanogram payloads and coming from nanogram probes that might be being launched towards us?
Yeah, I think both of those are important additions to SETI. We need to think out of the box in terms of all the ways that aliens could be communicating or intentionally or unintentionally. I mean, just sending a payload is actually a Bracewell probe, so it could be intentional, but they also could be very limited. So ideal sail would absorb most of that light. Maybe you could see the scatter from the source, and the probes that replicate on arrival may have very limited replication, partly in deference to ecosystems that may already exist there. So you want to replicate just enough to make a communications conduit. So they both might be very hard to detect, but of course, everything we're trying to detect is hard so far.
Yeah.
One last question there. So with these more radiation tolerant species that, possibly have limited function initially, if you were trying to do biological engineering and modify their DNA sequence to include additional information that would accelerate evolution or allow, particular function or form to be generated, like if we were trying to look for that signs of that in ourselves, how would we start?
Well, you could either go forward from a radiation-resistant organism to some new functionality, or you can take something that has the functionality you want and make it radiation-resistant. There is some experiments on making a very radiation-sensitive organism, E. coli, into something that's 10 to 100,000 times more radiation-tolerant with as little as 4 mutations. I'm not sure this has been confirmed by a lot of groups, but it's tantalizing that there may be ways of making organisms much more radiation resistant. They of course have to be working at a reasonable temperature and with some source of energy to do that. I think the issue of morphology and functionality, of creating new morphologies and new functionality that are not just cheating by, probing the entire biosphere for interesting things, is still an open question. I mean, it's a rapidly progressing field, but it's still, there's a lot to be learned.
Okay, so and I think now James and Jamie, it would be really provocative and quite interesting to see the results of our poll. So we had some questions related to the. Okay, so here we go. So the question: how would you harness energy to sail a spacecraft from Earth to the next star system? Photons versus fusion. It's about 70-30 for photons, 69 to 31. But still, I would say quite a sizable showing for fusion. I think so Michael, I think you have quite a quite a base of support out there for thinking further about fusion systems. And then the second is given the the journey to Alpha Centauri, should it be a flyby or should we build systems that decelerate and capture? Flyby wins, but not by a landslide, 56 to 44. And I think that indicates that both are really quite interesting. And I guess the question we can, as a panel, we can debate about the feasibility of the hit the brakes and capture, particularly for the light sail. It's an interesting question. And to send data back and forth, should we leave a trail of network beacons? And I'm looking forward to hearing Tom's thought about this, or construct a large ground-based transceiver and beam it up and beam it back. And that came out quite evenly. So maybe starting with the last question first and asking Tom to weigh in on this question. What do you think? Relay, communications relay, or beam up and beam back all in one go?
Communications relay introduces a lot of single point failures potentially. You could put multiple spacecraft at various distances, but in general, you're gonna have to overcome that R to the R squared loss in one way or another. And you can either do it portioning it a certain amount at each particular relay, or just trying the whole thing. And our efforts these days are still oriented on trying to get the whole distance in one fell swoop.
Yeah. Okay. Well, that's interesting. I guess. Yeah. When you think about making a system robust, single points of failure seem like a scary possibility. So actually, maybe I'll invite the panel to weigh in on question number 2 about the viability and the schemes for perhaps hitting the brakes and capturing. So Michael talked about this in the case of fusion and proposed some potential schemes. We haven't heard thoughts about this from the light sail point of view. Arthur, do you want to say a little bit about this? Is this a feasible scheme, or should we plan on sailing on by?
Well, sailing on by is definitely there for sure for light sailing. It's like naturally out there. The capturing is much more difficult because you need to compensate the velocity, which is very, very high, going from 20% of speed of light to something smaller. But I think what we see is that we haven't explored it enough. That's my impression. So if we kind of look into different options, like for example, some parts of the spacecraft being dedicated to slowing down, or some probes being separated and then thrown into the system, then maybe something can be out there. But this hasn't been explored as much. With fusion and other concepts, it's easier to think about because we sort of routinely do this type of capturing for interplanetary missions. We just send a spacecraft, then we know how to tailor our delta V and capture the spacecraft there and so on. For light sails, we haven't thought about it. So my concluding remark is that I see that it's possible, but I think that we didn't explore it enough.
Yeah, perhaps that's a thought for the future for the Starshot team to contemplate. And photons versus fusion. Maybe we can have our panelists weigh in here as well.
Well, the thing about fusion is going to be very difficult to get to a nearby star in a short period of time, which is even for a flyby, which is promised by light sail. Even if we're just comparing flyby, you're still with the technology that we think is reasonably possible. It's 500, 300, 250 years are going to be the kind of flight times you're going to expect with a fusion propulsion system. So if you can make the light sail work, you're going to get things a lot faster. The advantage of fusion, again, is even if you're flying by Alpha Centauri, you have a lot of power for sending back data and scientific instruments. So it's like any other scientific mission. You have to trade what the goal. Ultimately, you look at what are the goals, what data do you want to collect, and which propulsion system gives you what you want or closer to what you'd like to get.
So following up on that a little bit, I had, I think Mike's probably met one of my former students, Dr. Jim Clark. I had him look at what the delta V would be for a Hohmann transfer to the next star system, assuming you had kind of an optimal trajectory and infinite time. And it turns out it takes, hundreds of millions of years, but the delta Vs are on the order of tens of meters per second is all you need. You just need a lot of time. So, but that kind of brings us back down to like evolutionary and biological timescales. And, are we ultimately, if we can't come up with technologies that accelerate this, where's the happy medium? Tens of meters per second is not so bad. If I can achieve escape velocity, then it's only going to be tens of meters per second to get to the next star system if I've got 100 million years. It's kind of fun to think about in terms of, I don't know if Stephanie or George wanted to comment on, what could be out there transiting between star systems at very, at their own turtle paces and going back to like the tortoise and the hare here. Ultimately, this is probably already happening and we're just not super paying attention to it.
Like interstellar objects?
Yeah, or particles, or I mean, apparently it doesn't take a lot of energy to get between star systems if you can escape first, and then you've got 100 million years or so.
Maybe that's why we have interstellar objects coming and visit us quite often.
Yeah, there's some discussion on how these interstellar objects are getting ejected from their host systems. There's, the debate about, whether they've been bombardment, collisions, kicking things out, if it's during some crazy process of star or planet formation, think planet migration type things where, scattered disk happens and some of these objects just lose their trajectory. It's an interesting concept. And I think to answer your question or to address your question, Carrie, I think it's everything from soup to nuts. I mean, we have rogue planets, for example. So now we know interstellar objects, cometary, asteroidal-like bodies, and of course there's the dust. So.
Yeah, Stephanie, building on this, I thought maybe as we're getting close to the end of our hour here, and it's been a very, very lively discussion, what advice does a astrochemist and biologist have for a light sail design group? How should we design light sails to probe the interstellar medium? Are there experiments and instruments that we could build into the light sail that would help expand? What would be your wish list for us to design?
Absolutely. My wish list is beyond, I think, any agency is going to fund. I even asked to add things to JWST and they just laughed at me. So I think there's a lot of lessons learned from both heliophysics and planetary science as far as instrumentation for in situ type measurements, or even as we send things out there. But even, I will say, having more traditional astronomical observatory type instrumentation cameras, at various wavelengths, just the proximity in and of itself will give you a sensitivity that we don't have. And we even see that, for example, on planetary science missions. You know, we have orbiters that have infrared cameras that can see things that we can't see from the ground just because your column is now that much closer, right? So you're not dispersing the signal so much. So I think having, you know, particle detectors on some level, dust detectors on some level, mass spectrometers, just so we can get compositional studies, because we know that there's all kinds of crazy things happening on the surface of dust grains, and knowing if that's ubiquitous, it would be a very important as far as astrobiology and astrochemistry implications. Ion probes, I mean, magnetometers, you want to know magnetic fields. I mean, I don't think there's a limit.
You're going to put the mass spec in that star shade there, Stephanie. Is that possible? Can you put a mass spectrometer in the star shade?
I mean, they're small ones, right? We have sniffers that, you know, you can put on your keychain, I think. So it feels like it's something that could be potential, depending on where you're going, what you're going to interact with. But I definitely think having particle detectors and some sort of dust detector would be very, very, very interesting, as well as things like knowing the magnetic fields that you're going through, especially as you're crossing things like heliopause, stuff like that.
Well, I think that's a really great place to leave off here, which is really thinking about the collaborations between the journey and the destination, really thinking about how design of spacecraft and the light sail spacecraft in particular could, you know, beyond imaging and spectroscopy, taking pretty pictures, what we can do to build science instruments into these ultralight payloads. Yeah, that's a really, so thank you for providing us with that wish list that I'm sure our communications and light sail and Starship team will have to noodle on and get busy with.
Yeah, thank you, everyone. This has been a great discussion. I guess we are at our spot on the agenda where we need to stop dreaming and planning and get back to work and try to make some of this happen, right, Harry?
Yeah, that's right. So Tom, Michael, Arthur, Stephanie, really thank you. And George for a really provocative opening keynote. And I guess we'll pass it back to Pete Worden.
Many thanks, everyone. Just before we go to Pete Worden, if we could please bring on from NASA Ames Research Center, Penny Boston for some ending remarks here before we go to Pete.
Hi, folks. This has been quite a tour de force in only a day and a half. I just want to express my gratitude on behalf of Ames Research Center and how delighted we are to be part of the Breakthroughs Discuss excursions into the future possible, as I think of them. Nothing is more transformative, really, than investigating these great questions of science, particularly when they're melded with great exploration voyages and expeditions. Thinking back through history, of course, Darwin's voyages on the Beagle are one of the classic examples of this in our past. One could cite others. And so it seems to me that the direct interrogation of the AlphaSen system is a perfect case study that blends both of these powerful incentives of exploration and science magically together. You know, reflecting on our past year, and as we drag into a second year of the COVID pandemic, which for us as a species is itself a type of uncharted voyage with unprecedented feats of science and great acts of heroism, and frankly, a mixed bag in how well we've done. I am heartened, and I take it as a sign of our gradual and perhaps painful maturation as a species, that there are groups seriously entertaining questions in enterprises like Starshot to the Alpha Centauri system. This type of thinking, besides the goals in and of themselves, have profound impacts on the nearer term science and engineering enterprise that we're all about, serving as inspiration for the daily conduct of the more incremental progress that we make and that constitutes the vast bulk of our scientific and engineering work. I think of it as sort of a time-coupled reverse engineering of inspiration. For example, based on some of the comments that George made in his remarks, it makes me think that clearly the prospect of something like Starshot will help us to move more enthusiastically in the direction of what I call planetary protection friendly engineering methods and components. So once again, my congratulations to the Breakthroughs Discuss team and leadership for another wonderful intellectual feast. And we're looking forward to next year and what will be laid out for us then. So let me turn it back to you, Jamie, for Pete's closing remarks.
And Pete Warden, please.
Well, this has been a fabulous conference. I have learned an incredible amount. I'm always been excited about our nearby neighbors, particularly the Alpha Centauri system. And, I think we're going to learn a lot about it in the next decade. And then probably later this century, we're going to send probes there one way or another. Also, I'm very excited about the opportunities within our own solar system. We heard about that last night at the Yuri's night celebration. And the other thing, one of the highlights for me was James Cameron, who has made some of my most favorite movies, came on and shows we have huge interest by the artistic and film community. So I think this is going to be really fun, and we look forward to seeing all of you next year, hopefully in person, many of you. So for all of you, have a great day and a great year. And I'm hoping that 2021 will end up better than 2020 did with the COVID and everything. But Godspeed to you all. Thank you.
And on behalf of the Breakthrough Initiatives, we would like to thank you, all of the co-hosts this year, which is the Harvard-Smithsonian Center for Astrophysics, UC Berkeley Center for Integrated Planetary Science, and the NASA Ames Research Center. And of course, a large thank you to all of our staff at the Breakthrough Initiatives and Breakthrough Prize Foundation for making this a great success. So until next year, thank you.